Hey everyone, first up a very big thanks for actively tuning in to all our tech-oriented videos. Talking about tech, we bring you an exciting tech-savvy week with full-on cutting-edge tutorials based on software development. Starting from the fundamentals of data structures and algorithms to mastering the state-of-the-art frameworks and getting involved into the latest and trending projects for your portfolio. So, without any further ado, let's get started with our day one of the software development journey. So, on day one, we get to start with the fundamentals of software development, where we get to master the data structures. The data structures act as the foundation of any software program. It's important for the developers to have a comfortable understanding of data structures and learn the knack of implementing them in real time. The sole reason for which we have devised and strategically organized all the critical data structure tutorials along with the real-time examples in the learning order.
So how does algorithm work in real life? So we'll have a use case here. On my screen, we have a lady and she is Shreya. Shreya wants to make some tea and for that she is following some steps. So the first step is she'll take a pan and fill it with water and place it on a gas stove. Followed by that, the second step is she'll make sure that the water comes to a nice boil and then she adds some tea leaves and sugar. Followed by step 2, we have step 3 where she'll allow the leaf to be fully expanded and she'll add some milk after that. Next we have the step 4 where she will wait for the tea to come for a good decent boil. Next we have step 5 where she'll turn off the gas and she'll take the pan off from the stove and the tea is ready to get filtered. And lastly, we have the step 6 where she is all set with the tea. So in computer science, an algorithm is a method or set of rules that we must be following to perform some specific calculations or other problem-solving operations. As a result, an algorithm is a collection of rules or instructions that govern how a work needs to be conducted step by step to achieve the desired results. To accomplish a task, we first provide some input and then follow a sequence of steps to acquire the required outcome of the input. So that is the fundamental definition of an algorithm, and we also had a use case. And now we will move ahead and understand the characteristics of algorithms. So basically we have 6 characteristics of algorithm. So the first one is it should be clear and unambiguous. The second one is that it has to be well-defined inputs. And the third one is that it has to be having well-defined outputs as well. The fourth property of an algorithm is its feasibility, followed by that, finiteness, and finally we have language independence. Now, we will look into each one of the characteristics in detail. So first we have clear and unambiguous. So this statement is the one which states that the algorithm should be straightforward, simple, and easily readable. Each one of its steps should be distinct in every way and lead it to a single conclusion. So the next one is it should be having well-defined inputs. So this means that an algorithm should indicate what output can be expected as well as the input should be properly well-defined. Now we have the third one. Similarly, we should also have well-defined outputs. So the well-defined output characteristics of an algorithm means that the algorithm must clearly indicate what output can be expected as well as the output should also be well-defined. Followed by the third characteristic, we have the fourth characteristic, that is the finiteness of algorithm. So the finiteness of algorithm says that the algorithm must be finite and it must not result in infinite loops or similar situations. So followed by the fourth one, we have the fifth characteristic that defines about the feasibility of an algorithm. So feasibility of an algorithm states that the algorithm must be really simple, generic, and practical. It must be able to be executed with resources available. Now, the last characteristic of the algorithm is being independent of the language. So it means that the algorithm should be defined in such a way that it is completely independent of the language. It must be simple instructions that can be implemented using any programming language. So these were the 6 major characteristics of algorithm. Now let's move ahead and understand how to write an algorithm. Writing an algorithm does not have any hard and fast rules. Next, algorithms are never created to support a specific programming language. As we all know, algorithms should be capable enough to support the conditional statements such as if else, switch, etc. An algorithm should be capable enough to execute some of the conditional statements such as if else, switch, etc. And also it must be capable to execute the iterative statements such as for loop, while loop, do while loop, etc. We usually create algorithms in a step-by-step manner. However, this isn't always the case. After the problem domain has been well defined, algorithm writing is a procedure that is carried out. We build an algorithm to find a solution to a problem. A problem can be resolved in a variety of ways. Let's look at an example of how to write an algorithm. Consider the following scenario. We need to create an algorithm to determine the largest number among the three given numbers x, y, and z. As a result, the initial solution to the problem can be written in this manner. So we begin with reading all the three numbers, and in the second step we will have a condition that says if x is greater than y, we will proceed to step 4, else we will proceed to step 5. Next, in step 4, we establish a condition that if x is greater than z, then x is the largest of the three numbers. Otherwise, z is the largest. If y is greater than z, z will be the greatest number. Otherwise, y will be the largest number amongst all the three in step 5. And the procedure will be terminated. Let's have a look at what the next solution has to offer. In this algorithm, we begin by reading all the three variables, then compare all the three numbers in the third step to determine the largest number, which is if x is greater than y, then there is another if else statement that states that if x is greater than y, then x is largest. Otherwise, z is the largest. Then there's if else statement which says that if y is greater than z, then y is greater. Otherwise, z is the greatest of the three numbers. So this is how we have multiple solutions to the same problem. So after discussing these solutions, we will move ahead and understand algorithm analysis. The algorithm may be studied in two levels. First, before it is made, and then after it is created. The two analyses of an algorithm are as follows. The first one is priori analysis and the second one is the post analysis. So first we will talk about the priori analysis. Priori analysis refers to the theoretical analysis of an algorithm performed before its implementation. Before implementing the algorithm, other parameters such as processor speed might be considered, which does not affect the implementation component. Next, we will talk about post analysis. A practical analysis of an algorithm is called as posterior analysis, and it utilizes any computer language to build the algorithm. The purpose of this analysis is to determine how much time and space the algorithm takes to operate. Now, after being understood the algorithm analysis, we will be able to comprehend the algorithm complexity. Two methods can be used to assess the algorithm complexity. The first one is time complexity, which states that the amount of time required to finish an algorithm's execution is known as its time complexity. Followed by time complexity, the other one is the space complexity, which is calculated by the quantity of space required to solve a problem and produce an output of space complexity of an algorithm. Let's take a closer look at these complexities. Now we will begin with time complexity of an algorithm. The big O notation is used to express an algorithm's time complexity. The asymptomatic notation is used to depict temporal complexity of big O notation. The time complexity is mainly determined by counting the number of steps required to complete the task. Let's take a look at an example to understand this time complexity in a much better way. If we want to find out a multiplication of n numbers, we can do it by executing a loop from 1 to n, then calculating multiplication when the loop ends. Then multiplication holds the n numbers multiplication, and last we return the calculated multiplication. The loop statement's time complexity will be at least n, and when the number of n increases, the time complexity will also increase. While the code's complexity, that is, returns multiplication, will remain constant because its value is unaffected by the value of n, and it will obtain the result in every single step. Next, we will discuss about space complexity, which is expressed with big O notation. just as time complexity. These 4 items are stored in space complexity. It initially saves program instructions, then stores constant values, then stores variable values, and finally it keeps track of function cells, jumping statements, and so on. The sum of auxiliary space and input size is used to calculate space complexity. The extra space or temporary space used by an algorithm is referred to an auxiliary space. After learning about algorithm complexity, we will look at some of the algorithm's pros and cons. So let's start with the advantages of algorithms. Firstly, algorithms are easy to understand. Next, algorithms are step-by-step representation of a solution. And lastly, the problem is broken down into smaller bits or steps in an algorithm, making it easier for the programmer. Now, an algorithm also have various drawbacks, one of which being it takes long time to write, hence it is time consuming. Second con of the algorithm is algorithms make it harder to demonstrate branching and looping statements. So followed by the advantages and disadvantages of algorithms, we now enter into the final segment where we discuss the differences between algorithms and programming. So the first difference is that an algorithm is a type of programming. On the other hand, a program is more directly associated with the computer performing one or more tasks, but an algorithm is more of a notation, a technique for solving a problem. Now, let us discuss the second difference. An algorithm can be decoded or run by a human, whereas the program is only run or decoded by a set of compilers of the computer. Now, the third difference. Basically, an algorithm is a design of the solution to the problem. Here, we can only analyze the solution, but we can never run it. But whereas on the other hand, programming is completely a different ball game. Here, you can directly implement a certain phase or an entire program and test the programs and get an output. So the fourth and the last difference between an algorithm and programming is an algorithm is written using natural human vocabulary, whereas programs are written using any programming language such as C, C++, Java, Python, etc.
Now, let's get started with our first concept, that is, what are data structures? Data is an information that has been translated into a form that is efficient to movement or processing in computing. As it relates to today's computers and transmission media, data is an information that has been converted into binary digital form. The term raw data refers to the data in its most basic digital format. After defining data, let's look at what data structure entails. A data structure is a data organization, management, and storage format in computer science that allows for efficient access and modification. Or, a data structure is an algebraic structure about data that contains a collection of data values, their relationships, and their functions or operations that can be applied to the data. We will now understand why exactly we need data structures now that we have already defined what is a data structure. So, let us have a look at some of the data structure characteristics. The first one is, each data structure allows data to be stored differently. Following that, the data structure allows for more efficient data search and retrieval. Then, specific data structures are chosen to solve specific problems. Last but not the least, it enables the management of large amounts of data such as large databases and indexing services such as hash tables. Let us now look at some real-world examples of data structures. First and the foremost, we have the dictionary. Assume that we are looking for the word Simplilearn in the dictionary, and we know it begins with the letter S. So we can search for this word beginning with the letter S, and then this is an example of array data structure. As a result, this dictionary can also function like an array data structure. Following by that, we have a music player example. If you have a playlist with 3 songs, the second song will play after the first and the third will play after the second. So these will be played without any interruption because all these 3 songs are linked with each other using linked list type of data structure. So followed by linked list, the next example we have is the data structures. The stack of books analogy is a perfect example of the real-time working of the stack data structure. Subsequent to that, assume there is a line of people at a ticket window and the person who comes first gets the ticket. This particular movie window queue is an example for the real-time implementation of queue data structure. Last but not the least, Google Maps. Google Map is the graph data structure in which all the cities and states are connected. If we want to go from one place to another, there may be many ways to do so. So we can use some algorithms to find the shortest path. As a result, the Google Map is a perfect example for the graph data structure working analogy. Following that, we will look at some different types of data structures in this tutorial. So the first type is the linear data structure. The elements in the linear data structure are arranged subsequently one after the other. They are simple to implement because the elements are arranged in specific order. Followed by the first type, the second type is the non-linear data structure, which we will be discussing a bit later. So in linear data structures, we have 4 different types. The first one is the array data structure. Memory elements are arranged in a continuous order in arrays, and arrays elements are of same type. The software program also determines the type of elements that can be stored in arrays. So followed by arrays, we have linked list. Linked lists are completely similar to data structures. Data elements in linked list data structure are linked together by a series of nodes. Furthermore, each node contains the data items as well as the address to the next node. The third data structure is the stack data structure. Elements in a stack data structure are stored using LIFO principle. In other words, the last element stored in the stack is removed first. In stack, operations can only be performed in one end, namely the top. And the last data structure is the queue data structure. Unlike stack, queue data structure operates in the FIFO principle, which states that the first element stored in the queue is removed first. In a queue, insertion and deletion are carried out from opposite ends. Now we will discuss the second type of data structures, which are the non-linear data structures. The non-linear data structure is the second type of data structure. Non-linear data structures do not have elements in any order as opposite to the linear data structures. Instead, they are arranged in hierarchical order, with one element connected to one or more others. So the first one in the non-linear data structures is the tree data structure. A tree data structure is built using nodes and edges. Each element in the tree data structure is called as node or vertex. Each vertex or node is connected to the other nodes or other vertices using edges. And the second one in the list is the graph data structure. A graph data structure is completely like a tree data structure. It also has the vertices and edges. Each vertex in a graph data structure is connected using edges. The only difference between a tree and graph is that in tree you can have n number of vertices, but in graph you will have only 2 vertices. After discussing the graph data structure, we will move ahead into the last segment of this tutorial, that is importance of data structures. So the first one, data structures are widely used in almost every aspect of computer science, both for simple and complex computations. Next, data structures are used in all areas of computer science, including artificial intelligence, graphics, big data, operating systems, and much more. After that, the data structures are an essential component of many computer algorithms because they allow programmers to manage data efficiently. Lastly, a proper data structure selection can improve the efficiency of a computer program or algorithm.
There are various programming languages that you can learn to help you code data structures. We will discuss C language, C++, Python, and Java. Let's discuss them in detail. First up, C language. C is a general purpose structure programming language. C language can be used to develop programs like operating systems, compilers, databases, and so on. C language has a vast library that contains numerous built-in functions. Next up, C++ language. C++ is also a general-purpose programming language. C++ supports 7 styles of programming, like functional, structural, and object-oriented programming. It is also used in creating operating systems, browsers, and games, etc. Next up, Python programming. Python is the most significant programming language because the syntax of Python programming can be easy to understand to every learner's level. And this programming language is also loaded with the full of libraries that helps in implementing scientific computing. Working and deployment of Python are supportive and easy in any environment. Finally, Java programming language. In this modern era, Java is the best language to choose. Nearly thousands of applications, softwares, and development tools are built using the Java programming language. The technology is primarily used in creating websites such as YouTube, Google, Amazon, Flipkart, and many more. Moving forward, now that you have a better understanding of which programming languages you would like to code with, let's understand what are the prerequisites you need to learn to get started with the data structures and algorithms. First up, basic syntax. Before you start writing any code, you need to have basic syntax on your tips or you may run into various errors. Next up, data types. If you want to make your code perform various operations and you will need to understand data types and their syntax. Next up, operators, variables and functions. These are the elements that makes a code functional or operational. The data types are essential in declaring them. Next up, conditional statements or loops. Let's say if we want to print only a specific part of the information when certain conditions are met, then we can write conditional statements if else. If we were going to print a lot of elements like all natural numbers from 1 to 100 with a bit of code, then we can write some loops like for loop or while loop. Then we will discuss object-oriented programming. Object-oriented programming or OOPS is built around objects, which are data structures that contains both data and the code. Next up, we will discuss data structures. We will start with arrays, linked lists, stack, queues, trees, graphs, and heaps. Now let's have a closer look at them. First up, arrays. An array is collection of elements stored in consecutive memories. An array is the most basic data structures. The majority of data structure and algorithms can be implemented with the help of arrays. Next up is linked list. A linked list is a linear data structures made of nodes. These nodes are made up of two parts, data and the address to the next node. Linked lists are easier to work with and they are faster at insertion and deletion. Next up, stacks. Stack is a linear data structure that follows a particular order from which the operations are performed. We can perform insertion and deletion only from the top. This is also why stacks are called last in, first out or LIFO based data structures. In stack, insertion is referred to as push operation and deletion as pop operation. Next up, queues. Queues is also an abstract data structures, but unlike stacks, a queue is open at both its ends. One end is used for insertion, also referred to as enqueue, and the other is used for deletion, also known as dequeue. This is why the queue is regarded as first in first out or FIFO based data structure. Following, trees. A tree is a hierarchical data structure made up of nodes. The first node of the tree or the node which has no parents is called root node. Else all of the other nodes can have a maximum of one parent and can have multiple children. Each node contains some data and links to its children. Next up, graph. A graph is a non-linear data structure consists of nodes and edges. The nodes are sometimes also referred to as vertices, and the edges are lines and arcs that connects any of the two nodes. Graphs are often used to represent networks. Finally, Heap. A heap is a special case of trees. Heap is a complete binary tree, that is, it can have maximum of 2 children and all level except for the last level should be filled. A heap is of two types, max heap and min heap. When every node has a value greater than its parent, then the heap is called max heap. And when every node in a heap has less value than its parent, then that heap is called min heap. Now that you have a firm grasp of basic coding and data structures, we will discuss some algorithms. We will first discuss searching and sorting. After that, we will discuss divide and conquer. Then greedy algorithm, dynamic programming, and backtracking. Let's discuss them in detail. First up, searching. Searching algorithms are intended to search and retrieve an element from any data structure in which it is stored. Next, a sorting algorithm is used to rearrange the elements of an array or list based on the comparison operator on the element. Efficient sorting is critical for enhancing the efficiency of other algorithm that needs input to be sorted list. Next up, divide and conquer. This algorithm requires to divide the whole problem into sub-problems and solve them and then combine them back to get a complete solution. Some algorithms follow this approach like quicksort, merge sort, and Strandson's algorithm. Divide and conquer requires that there must be more than two subproblems. Next is greedy approach. The greedy algorithm aims to build up a solution by selecting the most beneficial option. Greedy is best suited to problems when picking the locally optimal also leads to a global solution. The greedy can also be used to solve Huffman coding, job sequencing, and knapsack problems. Next up, dynamic programming. A dynamic programming technique that produces smaller subproblems and then uses the subproblem solutions to solve the more significant problem. Dynamic programming is nothing but optimization of recursion problems. Simple optimization can change the time complexity from exponential to polynomial. Next up, backtracking. Backtracking is an algorithmic approach to recursively solving problems by attempting to develop a solution progressively, one piece at a time. Then discarding any solution that do not fulfill the problem's criteria at any point in time. Backtracking is also used to solve problems like n-queens, Sudoku, Hamiltonian cycle, etc. We have now discussed both data structures and algorithms. Now let's have a look at top coding contests or platforms to hone your skills. We will start with HackerRank, then CodeVita, Geeks Coding Challenge, CodeJam, and at last CodeChef. Let's discuss them in detail. First up, HackerRank. HackerRank is a technology hiring platform that is standard for assessing developer skills. HackerRank organizes various contests like RRank, Hackfest, and Hack the Interview. Next up, CodeVita. CodeVita is coding platform where one can compete against pupils from all over the globe for the world's best coder title. Tata Consultancy Services or TCS organizes CodeVita. Winners usually win prizes like cash prizes or free vouchers. It also opens up a door for career opportunities for its learners. Next up, Geek Coding Challenge. Geek Coding Challenge is a 3-day event organized by Geeks for Geeks. In GCC, learners can participate and challenge themselves in solving coding problems to win prizes. Next up, CodeJam. CodeJam is a Google-hosted and managed international programming competition. The competition consists of collection of algorithmic tasks that must be completed within a specific time limit. At last, CodeChef. CodeChef is a website that aims to assist programmers in succeeding in algorithms, computer programming, and programming competitions. CodeChef often organizes various contests like cook-offs and lunchtime. We have now discussed various coding platforms or competitions to hone your skills. First up, let's say if you can't solve a problem in under an hour, you should put it aside for the time being and move on. You can always return to it at a later time. Next up, even if you answer the question correctly, I recommend that you read the discussion and look at other solutions. You could come up with a better way to answer that question. Finally, if you are having trouble understanding a solution, then I recommend you to dry run of the code. Introduction to time complexity. The time complexity of an algorithm is the amount of time it takes to run as a function of the length of the input. The length of the input determines how many operations the algorithm will do. It will provide the information about the variance, increase or decrease in execution time as the number of operations in an algorithm increases or decreases. Next up, types of time complexity. We will start with the constant time complexity. Then we will discuss linear, logarithmic, quadratic time complexity. Now let's have a look at them in the detail. First, constant time complexity. When an algorithm is not reliant on the input size n, it is said to have constant time of order big O of 1. The runtime will always be the same regardless of the input. As you can see in the code, every line has the runtime of 1. And they are all independent of any input size, so the runtime is always constant. Next up, linear time complexity. When an algorithm's running time increases linearly with the length of the input, it is said to have linear time complexity. When a function checks all the values in an input data set, it is said to have the time complexity of order of big O of n. As you can see in the code, the loop depends on the size n, so the time complexity rose up to n. Next up, logarithmic time complexity. When an algorithm lowers the input data in each step, then it is said to have the logarithmic time complexity. Binary trees or binary search functions are some of the algorithms with logarithmic time complexity. As you can see in this code, by finding out the mid in every iteration, the runtime will decrease every step, making it approximately logarithmic runtime. Next up, quadratic time complexity. When the execution time of algorithm rises non-linearly up to n square with the length of the input, it is said to have quadratic time complexity. In general, nested loops falls into the quadratic time complexity order, where one loop takes big O of n, and if the function contains the loop inside the loop, then it multiplies. As you can see in this code, because of the nested loops, the time complexity rose to n square. Now that you have the firm grasp of time complexity and its type, we will discuss essential steps to evaluate the time complexity. To understand this, we will take an example of Fibonacci number. This code prints the Fibonacci numbers till n. We will divide this code into three parts, isolating all the loops that play a significant role in altering the time complexity. Let's look at the first part. It consists of some independent statement which give constant runtime for each statement. Next, let's move on to our next part, that is for loop. Since this loop runs n times, this will give linear time complexity on n. Next up, the third part, which also has the constant time complexity. Now, let's take a total of runtime, which comes out to be n plus 5. We will then discard the constant part to find the time complexity, which does not affect the overall time complexity. Now, we will have the final time complexity of big O of n. We have now discussed time complexity and how to evaluate it. Now, let's have a look at the time complexity of various algorithms. We will look at the time complexity of insertion sort, merge sort, quick sort, bubble sort, and some searching algorithms like linear search and binary search. Let's look at them in the detail. First up, insertion sort. As you can see in this code, we are using nested loops. So in worst case, its complexity comes out to be n square. Now in the best case scenario, the complexity will be linear time complexity. Next up, merge sort. In this case, whether it is the worst case or the best case, it will always remain n log n, as every statement in this code will run the same amount, so no matter what, its time complexity will remain the same. Next up, quicksort. The time complexity of quicksort in the best case is n log n, and in the worst case it is n square. Next up, bubble sort. As you can see in this code, we are using nested loops. So in the worst case, its complexity comes out to be n square. Now, in the best case scenario, the time complexity will become the linear time complexity, that is n. And after that, we will discuss some of the searching algorithms. First up, linear search. In the best case scenario, if the statement to be searched is at the first position, then the time complexity will come out to be constant. Whereas in the worst case, the time complexity will come out to be n. Finally, binary search. In the best case scenario, if the element is to be searched is at the mid, then the time complexity will come out to be the constant. Whereas in the worst case scenario, the time complexity will come out to be big O of log n. We have now discussed the time complexity and how to evaluate, and the time complexity of various algorithms. Now let's sum up what we have learned from this session. First up, the execution time increases with the types of operations we make using the inputs. Next up, the lesser the time complexity, the faster is the execution. Finally, if a code is of hundreds of lines, then it takes a toll on the PC's processor. So it is essential to check and reduce the time complexity as much as we can. Let's get started with what are pointers. A pointer is a variable that points to an address of another variable. It is declared using a star symbol, also called asterisk. And then we allocate a memory of a variable to it. We can access a variable's address using the ampersand symbol in the same manner as the pointer declaration. Let's write a code. We will declare a variable a is equals to 5 and a pointer ptr. Then we will assign this variable a's value to pointer ptr. Now let's write a print statement to directly access the variable's value using variable name. Let's write another print statement to print the value of a using pointer. Let's try and execute this program. As you can see, we have successfully accessed variable's value using both variable name and pointers. Let's get back to our slides. Now, let's discuss different types of pointers. First up, null pointer, void pointer, while pointer, and dangling pointer. Let's discuss these in details. First up, null pointer. It is a kind of pointer that points to a null memory. As you can see in the figure, here is a pointer which is pointing to a null memory. To get a better understanding, let's try a simple program in the code editor. Let's write a code. First we will declare a pointer var. Then we will assign its value to null. Now let's try to print this statement. Let's execute this. As you can see, since this pointer points to a null or nothing, that's why it doesn't print anything. Let's get back to our slides. Next, void pointer. When a pointer is created with data type void, then this pointer is called void pointer. If we want to print the variable's value, then we have to typecast this pointer to avoid any error. For better understanding, let's get back to the code editor and try it with a simple code. First, we will declare an integer variable a is equals to 5 and a void pointer ptr. Now we will assign address of a to pointer ptr. Let's write a print statement to print this pointer. Let's run this program. As you can see, we are getting an error. That's because we can't print a void variable. To print this, we have to typecast this variable to integer. Let's do this. We can typecast a variable like this. Now let's print this. As you can see, we can print it now. Let's get back to our slides. Next, while pointer. When we create a pointer but don't initialize it by assigning any memory to it, then this kind of pointer is called while pointer. These pointers can be very tricky. They can even cause a program failure or a segmentation fault. Let's get back to the code editor and try it with a simple code. First, let's declare a pointer ptr. But we will not assign it with any address. Let's write a print statement to print it. This time we will directly print it. Let's execute this. As you can see, we are not getting any results because there is no value assigned to it. Sometimes it may even throw segmentation error. Let's get back to our slides. Next, dangling pointer. Let's suppose there is a pointer p which is pointing at a variable. Now, if we deallocate this memory using a free function, then this pointer will point at a free space or a non-existing memory. Then this pointer will become a dangling pointer. To get a better understanding of this pointer, let's try it with a simple code. Let's declare a pointer ptr. Here we will dynamically allocate memory using a malloc function. To do this, we will put int star in a bracket Then malloc function. Then in another bracket, we will put memory size to be allocated. Now let's declare a variable a and assign its address to the pointer. Now to make it a dangling pointer, we have to deallocate the memory of this pointer. We will use free function for that. Now let's write a print statement to print this pointer. Let's execute it. As you can see, since we have deallocated its memory, that's why it is pointing to nothing. Hence, it doesn't print anything. Let's get back to our slides. Till now, we have discussed pointers, ways to access variables, and types of pointers. Now, let's talk about use cases of pointers. We will talk about pointer arithmetics, pointer to pointer, array of pointers, call by value, and call by reference. Now, let's dive right into it. Let's talk about pointer arithmetics. We can use four arithmetic operations on pointers: increment, decrement, addition, or subtraction of an integer from a pointer. Since pointer operates on addresses, it only makes sense if we apply pointer arithmetics on sequential data structures like arrays or strings. Let's discuss them in detail. First up, increment. If we apply this operator on a pointer, then it will shift this pointer's address to its sequential successor. As you can see in the figure, as we increment the pointer's value, we shift to the next index of the array. Let's get back to the code editor and try it with a simple program. Let's declare an array of size 3. Let's give them some value. We will then declare a pointer and assign it to the array's first element. Now let's write a for loop to traverse this array. In this for loop, we will increment a pointer's value and print this pointer's value to traverse this array. Let's try and execute this program. As you can see, we have traversed this complete array. Let's get back to our slides. Next, decrement. If this operator is applied on a pointer, it will shift this pointer's address to its sequential predecessor. As you can see in the figure, as we decrement this pointer, we also shift to array's previous index. Let's get back to the code editor and try to implement it. let's declare an array of size 3 and assign it some values. Now let's declare a pointer and assign array's last element's address to it. Now let's write a for loop to traverse this array. In this for loop, we will decrement the pointer's value. Also, we will keep printing this pointer's value to traverse this array. Let's try and execute this program. As you can see, we have traversed this complete array from the back. Let's get back to our slides. Next, the addition of an integer to a pointer. If this operator is applied on a pointer, it will leap forward accordingly. If the integer is 2 and our pointer points at the first element, then the pointer will sequentially skip one element and shift to the next element. Let's implement it in the code editor. Let's declare an array of size 7 and assign them some value. Then declare a pointer and assign it to the array's first element. Now let's take an integer n to add in the pointer. Now let's write a for loop to traverse this array. In this for loop, we will increment the pointer's value with integer n and we will keep printing the pointer ptr's value. Let's execute this code. As you can see, we have traversed this complete array skipping one element at a time. Since we have skipped 3 elements, that's why we are getting last 3 values as garbage values. Let's get back to our slides. Next, subtraction of an integer from a pointer. If this operator is applied on a pointer, then accordingly it will leap backward. If the integer is 2 and our pointer points at the last element, then the pointer will skip one element and shift to the previous element. Let's try and implement it in the code editor. First, let's declare an array of size 7 and assign it some values. Then declare a pointer ptr and assign it to the array's last element. Now let's take an integer n to subtract from the pointer. Now let's write a for loop to traverse this array. In this for loop, we will decrement the pointer's value with integer n. Also, we will write a print statement to print this ptr's value. Now let's try and execute this program. As you can see, we have traversed this complete array from back, skipping one element at a time. Since we have skipped 3 elements, that's why we are getting last 3 values as garbage values. Let's get back to our slides. Let's talk about precedence of these operators. Operator asterisk and ampersand have the same priority as the unary operator increment and decrement. These operators are evaluated from right to left. Let's understand this concept with an example. Suppose if a pointer p points to a variable x, then we can swap x with pointer p in that expression. In the first row, we have y is equal to x plus 1, which means we are storing an incremented value of x in y. Similarly, if we replace x with a pointer p, we can store incremented value of pointer in y. In row 2 and row 3, we are incrementing x and storing incremented value in x itself. We can do this with pointers as well. In row 4, we are attempting to execute pre-increment with a pointer p. In row 5, we are attempting to execute post-increment with pointer p. Here we have to put star p in braces because these operators are evaluated from right to left. So to give more priority to pointer p, we have to use braces as they have highest priority. Let's talk about another use case, pointer to pointer. Basically, in this situation, a pointer will point at a variable via another pointer. We declare it with two asterisk symbol. Let's discuss it with an example. Suppose a pointer 1 points to a variable and another pointer 2 points to that pointer 1. This way, pointer 2 will indirectly be pointing to the variable. Let's go to the code editor and try implementing it. First, we will declare a variable var a pointer ptr1 and a pointer to this pointer ptr2. Then we will assign this variable var's address to ptr1 and ptr1's address to ptr2. Now we will write a print statement to print variable var, ptr1 and ptr2. Now let's try and execute this program. As you can see, ptr1 and ptr2 shows variable var's value as ptr2 is pointing to ptr1 and ptr1 is pointing to that variable. So indirectly ptr2 points to the variable var. Thus it prints the variable's value. Let's get back to our slides. Let's discuss the array of pointers. As the name suggests, it is an array that has all its elements as pointers. These pointers can be pointing at another array. It is declared as an array with asterisk symbol. Let's discuss it with the program. First, we will declare an array A of size 3. Then we will declare a pointer array ptr of size 3. Now we will write a for loop to assign A's element's address to ptr's element. Then we will write another for loop to traverse ptr and print its element. Let's try and execute this program. As you can see, it prints the value of array A's elements because array ptr's elements are pointing to array A's elements. Let's get back to our slides. Next, call by value. We don't use pointers in this concept, but it is very important to understand this concept to get better understanding of the next topic, call by reference. In call by value, we call a function and directly pass the variable's value as parameters. In this situation, a copy of those variable is created and get passed into a function as parameters. If we modify these parameters, it will not affect actual variables. Rather, these copies will get deleted as soon as the function body ends. Let's try implementing it in the code editor. Let's write a code. First, we will declare a variable x equals to 100. Then we will write a function call to function func with argument x. Next, we will write a print statement to check if any changes happened due to the function. Now let's write definition for this function. We will take a void function with argument as x. In this, first we will set x equals to 200. And then we will write a print statement to print this value. Let's try and execute this program. As you can see here, when we get back to the main block from function, its value again reverted back to 10. Because in call by value program, we only pass variables copy into the function, not the actual variables. Let's get back to our slides. Next, call by reference. In this, if we call a function, but this time we pass the variable's address as parameters, then in this situation, actual variables will get passed into the function as parameters. If we modify these parameters, it will modify the actual variables even outside the function scope. Let's try implementing it in the code editor. First, we will declare a variable int x equals to 100. Next, we will write a function call for function func with argument as address of x. Then we will write a print statement to check if any changes happen due to the function. Now let's write definition for this function. It will be a void function with argument as pointer x. In this, we will first set x equals to 200. Then we will write a print statement to print this value of x. Now let's try and execute this program. As you can see, this time variable x's value didn't revert to 100. That's because in call by reference we pass actual variable's address to functions, so it will modify them as well. Let's get back to our slides. During the course of this video, we have learned a lot about pointers. Let's discuss some advantages of the pointers. First up, pointers are useful to access a memory location. Pointers are also an effective way to access the array elements. Pointers are used for the dynamic memory allocation and its distribution. Pointers are also used to build complex data structures like linked list, graph, tree, stack, queue, etc. Now, let's talk about some disadvantages as well. First up, pointers are difficult to understand, so a programmer needs to be careful while handling them. They might raise some errors like segmentation error or access some unrequired memory and cause program failure. If a pointer is pointing to an incorrect value, then it might corrupt memory. Pointers may also cause memory leakage. Also, pointers are slower than variables.
So to understand this, let's go through a simple concept. Let us imagine that we have some data and the data is related to students, right? So if we wanted to store the marks of individual students, then we had to declare a variable for each of the student. So you can see we have student 1, student 2, student 3, 4 and 5 and their individual scores. So the score 1 is assigned to student 1 and so on, with student 5 being assigned to score 5. So in the real time, this might be a little clumsy. We have here just 5 students, so that is okay. But what if we had 500 students or 5,000 students, right? That might be an issue. There we have to create some 500 or 5,000 variables, and it would be a little tough to handle that, right? Even if we wanted to apply some operations collectively on all the variables, that might be a little tedious. So what if we had one variable which could store all the 5 students or 500 students or 5,000 students all together and make it really easy for us to apply some operations collectively on all the students, right? This sounds a little bit logical. So similarly, we do have a data structure which can do that, which can collectively store all the data elements in it as a single variable. And it will also help us to apply the operations which are logical or mathematical on all the variables and their values together as a whole. So that is the purpose why we had created arrays. That is the purpose why we needed arrays. So far we have understood what was the necessity for arrays. Now we will understand what exactly are arrays. So basically an array is a linear data structure that stores the elements in a sequential manner, one after the other. And when you declare an array, the variables will be stored one besides the other, that is adjacent to each other in a sequential order. Now let us understand how the array is represented by the compiler. Now the next part, that is the memory representation of arrays. Now let us imagine that we have declared an array which stores character type data. And another important point to remember about arrays, when you declare an array, it stores only a single data typed elements only. For example, here we have declared a character type array, right? So we cannot store integer type data or float type data in it. We only have to save character type array or character type elements in this particular array. So now let us imagine that we have created an array which is of character data type, and these are the elements which are A, R, R, A, Y. Now how does the compiler represent it in the form of memory? So when you create an array, these are formed, that is the index values and the address. So basically compiler will select a block of memory and it has addresses to that block, and it can be anything, right? Here we have 11, 12, 13, 14 and 15, and in real time it might be 1001, 1002, 1003, 1004, 1005. The main motto is assign a sequential block of memory, and this is the array and the elements are A, R, R, A, Y, and this particular one, which is the last one, is the index of the array, that is the position of the array for user. So using this index you can access the elements in the array. More on that in the accessing part. So let us imagine that we wanted to access the element R. So how to access it? We might not know the address, right? In that instance, we will use the index. This is for R reference. So we will tell, I want the element from array index number 2. And then we'll have the ARR, R element. So in the practical form, this is how we use the index. Now let's continue with the lower bound and the upper bound. So the first initial location is called as the lower bound, and at the last or the max value of the array is called as the upper bound. Now let us jump into the next topic where we will understand the different types of arrays. So these are the different types of arrays: one-dimensional arrays and multi-dimensional arrays. In multi-dimensional arrays, we have two more types, that is two-dimensional arrays and three-dimensional arrays. So how are arrays different from each other, right? So the first one, we'll deal with the first one, that is the one-dimensional array. Now, how is an array declared as one-dimensional? For that, we need subscript. So one-dimensional array requires only one subscript to specify the number of elements in an array. So how is it actually represented? So here you can see an example right on my screen. So here is how a one-dimensional array looks like. So here we have the data type, that is integer data type, and marks is the name of the array, and this is the size of the array. And here the elements will be stored, and here it is the index value of the array. And remember, the index value of array always starts from 0. In the previous example, that was only for basic understanding, so I just started that with 1. In the practical way, the array index always starts from 0. So followed by the one-dimensional array, we will deal with the multi-dimensional arrays. In that, we have the following. The first one is the two-dimensional array, and the second one is the three-dimensional array. In the multi-dimensional arrays, we require more than one subscript. In the previous example, we had one-dimensional array, so the subscript is just 1, that is 10 columns, right? So we just had one single row and 10 different columns. But in the multi-dimensional arrays, we need multiple rows and multiple columns, right? So we need 2 subscripts for two-dimensional array and more than 2 subscripts for three-dimensional arrays. So first we have the two-dimensional arrays. The 2D array is organized in the form of a matrix, which can be represented as a collection of rows and columns. So here is the example. As you can see on my screen, we have 3 columns and 3 rows. And we have 2 subscripts that define the number of rows and the number of columns and the elements in each and every row. So the 1, 2, 3 confines the first row, 4, 5, 6 confines the second row, and 7, 8, 9 will be the third row. Now similarly, we have three-dimensional arrays. A 3D array is a collection of 2D arrays which consists of 3 subscripts: block size, row size, and column size. So here we have an example for that. So we have 3 subscripts, that is, the first one is block size, the second one is the row number, and the third one is column number. So this happens to be the first block, this happens to be the second block, and this is how a 3-dimensional array can be represented. Now we have the next stage where we will understand how to declare the arrays, and the syntax is right on my screen. You need to specify the data type of the array, which is integer, float, or character, or any selection which you make. Followed by that, you need to select an array name for your array, and inside that you need to declare the array size. And sometimes you can also eliminate the array size if you wanted to, have a dynamic array. And here is an example for that. You have integer data type, name of the array is example, and the array size is 6. So the compiler will allocate continuous memory block of 6 integer type blocks. So these are the few more methods to initialize the array. So here you can see integer data type, array name is A, element size is 5, and we have 5 elements. The method 2 is, remember I have said you can eliminate the size of the array, right? So here you can use this way as well, integer data type, array name A, and no size here, and you can directly declare the elements. And the method 3rd. So here you have the name of the array, size of the array, and you are allocating the elements to the individual memory locations. This is also another method to initialize array. And method 4 is using a for loop. You can just initialize a for loop and the I value will be stored in the array locations starting from 0. Now let us understand how to access the elements in an array. So to access the elements in an array, you need to specify the name of the array and memory block where you have that element that you want to access. So here we have an example, which is integer data type, name of the array is xyz, and the element we wanted to access is 5. So here we have an example that is integer type array name is xyz, and it has the size 5. And now we wanted to access the first element in an array. That can be done using the first index, that is xyz of 0 index, that is the first element, and accessing the second element, and so on. xyz of 1 will be the second element, xyz of 2, 3, 4 will be the third, and 4th and 5th elements. Now let us understand some basic operations that can be performed on the array elements. So the following are the operations that can be performed on the array elements, that is the traversal, insertion, deletion, searching, and sorting. Now let us get into practical mode and try to execute some examples based on traversal of the array, insertion of an element into the array, deletion of an element from an array, searching for an element in an array, and sorting the complete array. So at first we'll carry out the traversal operation. So here we have an array that is A of 5 and the elements are 1, 2, 3, 4 and 5. Now we're going to use a for loop to traverse through this array and print all the elements sequentially. Now let us execute this code and see the output. So as you can see, the code got successfully executed and the elements, that is 1, 2, 3, 4 and 5 from the array A are printed sequentially. Now moving ahead, we'll try to execute some examples based on insertion of element into the array. So on my screen you can see an example for inserting an element into the array at the starting position of the array. Now let us try to execute this code and see the output. Don't worry about the codes. These code documents will be attached in the description box below and you will be able to have an access to it and run these codes in your personal laptop and get a better learning experience. Now you can see the code got successfully executed and now it is asking for the size of the array. Let's declare it as 5 and now let's enter the elements into the array. Now it is asking for the element to be added at the beginning of the array. Now we have 2, 3, 4, 5 and 6 existing in the array. Let's add the first element 1 and there you go. The resultant array is 1, 2, 3, 4, 5 and 6. The element which we added at the ending, which is 1, is supposed to be in the first or the beginning part of the array, which is here at the first index location as planned. Now let's get started with another example on the insertion. Now let's try to insert an element at any given location as per the user's choice. So as you can see, we have a program on my screen and running this program must help us to insert an element into any given location of the array. Now let's try to quickly run this program and see the output. So there you go. Enter the elements into the array. Let's enter 1, 3. Let's try to run this program and see the output. So there you go. The program got successfully executed and now the output is asking for us to tell it the number of elements in an array. Now let's say 4 elements. So now let's enter the 4 elements. 1, 3, 4, 5 and 6. Okay. So the 4 elements, which is 1, 3, 4, 5 are been inserted. Now it is asking for the location where you want to insert the element. Now let us insert it in this second location. Now let us set the value as 2 and there you go. The resultant array is 1, 2, 3, 4 and 5 and the element, which is 2, was supposed to be added in the second location and it has been successfully added. Now let's try to execute another example based on insertion where you will try to insert the element in the last position. Now this program on my screen will help us to add an element at the end of the array. Let's quickly run this program. Now it is asking for us to enter the 5 elements of the array. Let's enter that. Now it is asking to enter the element to be inserted. Now let us enter the element and this element should be added at the end location as discussed. The resultant array is 1, 3, 5, 7, 9 and 11. Now let's continue with the deletion operation. Now the program on my screen is an example for deleting an element from the beginning position of an array. Now the program got successfully executed and it's asking for us to enter the size of the array. Let's enter the size as 5. And now let's enter the elements of the array, that is 1, 2, 3, 4 and 5. Now the element from the first location, that is 1, has been deleted, and the resultant array is 2, 3, 4, and 5. Now the code on my screen will help you to eliminate the element from the ending location of an array. Now let's try to quickly run this program and see the output. So you can see that the program is successfully run and it is asking for us to enter the size of the array. Let's enter 4. Now let's enter the elements of the array, that is 1, 2, 3, and 4. Now after eliminating the last element from the array, that is 4, we have the resultant array, that is 1, 2, and 3. Now a little homework for you guys. Let's try to execute an example for deleting an element from any location of an array. This will be a homework. Now don't worry, try on your own, and if you don't get that, you can refer to the comment sections below where you have the code document attached in the description box and you can refer to it. Now let's continue with the next operation where we will search for a given element in the array. So you can see that on my screen we have an example which will help us to sort the elements in an array. Let's quickly run this. So there you go, the program got successfully executed and now it's asking for the array size. Let's enter 5 and now let's enter the elements in a random order. Now the resultant array should be sorted. So there you go. The array after being sort is 2, 3, 5, 14, and 21. So there you go, the array got sorted. So now we have finished our practical session. Let's have a quick overview again. So traversal in an array is a process of visiting each element once. Traversal can be done by various means, that is by counting the array elements, printing the values sorted in the arrays, and sum of all elements present in the array, and many more. So this is how we traverse our array from the first location to the last location. Again, the insertion operation. Insertion in an array is a process of including one or more elements in an array, and it can be done at the beginning, at the end, and at any given index of an array, which we executed for all the 3 types of examples. Now next we have the deletion operation. So deletion operation or deletion of an element is a process of removing a desired element and reorganizing the array, and it can be done at the beginning, at the end, and at any given index. So we have executed the example for at the beginning and at the end, and the homework was at the given index. Don't worry if you don't figure it out, you can always refer to the example document which is mentioned in the description box below. Now the search operation. Searching is a process of finding a given value in the list of values, and it decides whether the search key is present in the array or not, and we have executed an example on that. And again, the sort operation, where we will sort the given array. If the given array is not in the default order or in a given order, that is ascending or descending, then we can sort the order of the array by the user's choice, given it is ascending order or descending order. Now in the next section of the tutorial, we will discuss the advantages of using arrays. So the first one is array stores multiple elements of same data type with same name. Next one, elements in an array can be accessed randomly using just the index number. Array memory is predefined, so there is no extra memory loss. Array avoids memory overflow. And finally, 2D arrays can represent the tabular form of data in a very efficient way. Now let us also have a look on some of the disadvantages of using arrays. The first one, the number of elements in an array should be always predefined. So there is no chance that you can add some extra element in the last moment. Array is static in nature, so its size cannot be varied after declaration. What if, consider that you wanted to store 10 student data in one array and you end up having just 7 students. So the remaining 3 is a waste, right? So you're wasting memory there. That's the problem. And insertion and deletion operations in an array is quite difficult as the array stores elements in a continuous form. And finally, allocating excess memory than required may lead to memory wastage. Now we have the final key takeaways of the arrays. So we discussed why do we need arrays, then we discussed what are arrays, followed by that we discussed types of arrays, next we had a declaration of arrays, accessing elements from an array, initializing the arrays, and basic operations on array, that is the practical demo part, and finally we have discussed the advantages and disadvantages of using an array. So we will see a brief definition of arrays. The array is a data structure that stores elements of the same data type in a sequential order. Two-dimensional arrays are considered as an array of arrays. Two-dimensional arrays represent the information in the form of rows and columns, which is completely similar to a tabular form of data. Following by the definition and briefing of the two-dimensional arrays, we will understand the need for two-dimensional arrays. So the main advantage of using a two-dimensional array is the elements can be represented in the form of a matrix, that is rows and columns. Using two-dimensional arrays, we can initialize, access, and print multiple elements in the matrix form by just running one single code segment. You can see an example right on my screen here. This is an example of marks list. Suppose a class has 3 subjects, namely English, Science, and Maths. We have 4 students and we wanted to represent the data in the form of a database. So here, the marks of the 4 students can be represented using two-dimensional arrays. Now, we will see the syntax of a two-dimensional array. So here, the syntax. At first, we need the data type. The data type can be integer, character, float, string, etc. Then we have the name for the two-dimensional array. And later, we can have 2 subscripts which represent 2 dimensions, that is the rows and columns. The first subscript defines the number of rows and the second subscript defines the number of columns. And note that the column number can never be null. And the end, we have a semicolon to terminate the syntax. And here we have some examples of two-dimensional arrays. So in the first example, we have the name of the two-dimensional array and we have 3 rows and 4 columns. And followed by that, we have another example which is of character data type and the name of the array is names and we have 7 rows and 15 columns. Next, we will see how to visualize two-dimensional arrays. We read earlier that two-dimensional arrays are a collection of rows and columns. Let's see an example of two-dimensional array. We will consider an array with 6 rows and 4 columns. As you can see on my screen, we have integer type array and the name of the array is array and we have 6 rows and 4 columns. The product of rows and columns will give us the total number of elements present in a two-dimensional array. In the current example, we have 6 rows and 4 columns and the product is 24. So we must have 24 elements in this array. Next, we will see how to initialize two-dimensional arrays. So there are 2 ways to initialize a two-dimensional array. So in the first method, we declare the elements in the set of curly brackets. This array consists of 3 rows and 3 columns. Note that the index always starts from 0. Here we have 3 rows. It means the row starts with 0 and ends with 2. The same goes for the column, but sometimes this method might be a little confusing. So we have a better method. The advantage of this method is clarity. We can visualize all the elements with better clarity compared to the previous method. So the first 3 elements are 9, 6, and 1. They are present in the first row. And in the second row, we have 144, 70, and 50. They comprise the second row. And finally, the third row in which the elements are 10, 12, and 78. So far, we have learned how to visualize and initialize a two-dimensional array. So we have done it by using the index values, that is the row index and the column index. So the row index value was 3 and the column index value was 3. For accessing an element in the two-dimensional array, we need to pass the name of the two-dimensional array followed by the row index value and the column index value. For example, Let us assume that we wanted to access the element 9. For doing so, we will pass the name of the array followed by the row index value and the column index value as shown below. That is int first 0, 0. And an important point here is indexing always starts with 0. We will now start printing the two-dimensional arrays. So to print a two-dimensional array, we will be using two nested for loops. So to understand the process of printing the two-dimensional array, let's get back to the practical mode and we will work on a code. So on my screen you can see an example for two-dimensional array. So here we have declared an array with the name first and we have 3 rows and 3 columns. And inside that, the first row of elements is 9, 6, 1 and the second row of elements is 144, 70 and 50 and the third row of elements is 10, 12 and 78. Followed by that we have two counter variables which are I and j. So we are using the first counter variable I in the outer for loop and the second counter variable j in the second inner for loop. And inside the inner for loop we have a print statement which is used to print the elements in the array. Now let us try to execute this code and see the output. So you can see the code got successfully compiled and we have our elements here, which is 961, 144, 70, 50, 10, 12 and 78. Now let us understand the logic. So here we have declared the counter variable as 0 and the condition is I should be less than 3, which is true. So the control will enter into the second inner for loop. Here we have j is equals to 0 and j should be less than 3, which is true. So here the condition or the statement is valid and it will print the first element 9. Followed by that j will be incremented again. J is now equals to 1 and j is less than 3. So again we'll print the second element 6. Again j value will be incremented to 2, so 2 is less than 3. Then we will print the third element, that is 1. Now when you increment the value of j from 2 to 3, the condition will fail because 3 cannot be less than 3. So the control will enter into the outer for loop. Here we have I value is equals to 0, which will be incremented to 1. So 1 is less than 3. Again, the control will enter the inner for loop. Here again, we will check for j is equals to 0, which is true. So we will print the second row of elements, that is 144, 70, 50, in the same way how we printed the first row, right? So j will be equals to 0. So then we'll print the first element. So j will be incremented to 1 and 1 is less than 3. Then we will print the second element, that is 70. And again, j will be incremented to 2 and 2 is less than 3. So we will print the third element, that is 50 in the second row. And again, j will be incremented to 3 now. The compilation of the condition will result in false. So it will exit the second for loop and it will come back to the first outer for loop. Now the value of I will be incremented to 2. So 2 is less than 3. The control will enter into the inner for loop again. Then we will print the third row of elements. That is 10, 12 and 78 in the same way how we printed the first row and the second row. After printing the third row, the condition will fail when j value is incremented to 3 and it will enter the outer for loop. Here the I value will be incremented again from 2 to 3 and the condition fails. Now the overall control will come out of both the for loops and it will terminate here. So that's how we got 9, 6, 144, 70, 50, 10, 12 and 78. So with that we have come to the conclusion, and so far we have learned the following things. What are two-dimensional arrays? Why we need two-dimensional arrays? Syntax of 2D arrays, visualizing 2D arrays, initializing 2D arrays, accessing 2D elements, and finally print the elements of two-dimensional arrays.
Let's get started with what is linked list. A linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. Typically, a linked list starts with a head node, which goes all the way up to the last node, which is called tail. Next, let's discuss why do we need linked list. A linked list is a linear data structure like arrays, but an array can only offer a fixed size, whereas a linked list can dynamically increase its size. Also, operations like insertion and deletion are much easier in a linked list than in an array. Now, let's try to implement the linked list in the code editor. Let's start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these four nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use head, same arrow formation and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to n2. N2 arrow data is equals to 5. N2 arrow next, 2 arrow next is equals to tail. Now tail is equals tail arrow data equals to 7 and tail arrow next is given null. Now let's call a function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then cout is a data and L. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. Now let's discuss different types of linked list. The first are single linked list. Next is the doubly linked list, the circular linked list, and finally we have the circular doubly linked list. Let's discuss each one of these in details. First up, single linked list. It is a unidirectional linked list. While using the single linked list, we can only traverse it in one direction, that is from head node to the tail node. Next up, doubly linked list. It is a bidirectional linked list. We can traverse it in both the directions. In this linked list, the node has an additional pointer that points to the previous node. Next up, circular linked list. It is a regular linked list except for its last node points to the head node. Programmer needs to be careful while traversing it, or they might get stuck in an infinite loop. Next up, the circular doubly linked list. It is a combination of doubly linked list and a circular linked list. Its last node points at the head node and the previous pointer of the head node points to the last node. It is also bidirectional linked list so that we can traverse it in both directions. We have now discussed the linked list, why do we need linked lists, and types of linked list. Now let's learn about some operations we can apply on linked list. We can use majorly two operations on linked list. First up, insertion and deletion. We can perform these operations in three different situations. First, at the beginning, at the last, or at a specific position after a node. Next, we will discuss these operations in detail. First up, insertion. We will discuss first insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give the new node's address to the last node's reference pointer. Next up, insertion at a specific position. To do this, we will have to change the reference address of the previous node to the new node's address and the new node's reference pointer to the next node's address. Now let's discuss deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to the null. Next up, deletion at a specific position. We will change the reference address of the previous node to the next node's address. We have learned a lot about linked list during this session. Now let's discuss some benefits of linked list. First up, a linked list is a dynamic data structure. That is, we can dynamically increase its size. Next, it offers easy insertion and deletion than other linear data structures like arrays and string. Since it can dynamically increase its size, resulting in no memory wastage. Next, it is pretty handy in implementing complex data structures like stacks and queues, etc. Now, let's talk about some disadvantages as well. First up, since the linked list is made up of nodes, it takes extra storage for storing data and reference pointer. Next, the traversal in the linked list is a bit harder than other data structure. Reverse traversing is easy in doubly and circular doubly linked list, but since it uses one extra pointer, it takes extra storage, making it another limitation. Let's get started with introduction to singular linked list. A single linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. These nodes can be traversed using pointers. It starts from the head node all the way up to tail node. Now let's try to implement the single linked list in the code editor. Start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these four nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use head, same arrow formation, and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to N2. N2 arrow data is equals to 5. N2 arrow next, 2 arrow next is equals to tail. Now tail arrow data equals to 7, and tail arrow next is given null. Now let's call up function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then out is a data and L. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. We have now introduced the single linked list. Now let's discuss some of the operations we can apply on a linked list. First up, insertion. We can perform insertion at 3 different situations, like at the beginning, at the last, or at a specific position after a node. Next up, deletion. Similar to the insertion, we can perform it in 3 different situations as well, at the beginning, at the last, or at a specific position after a node. Let's talk about them in detail. First up, insertion at the beginning. To execute this, we have to give first node's address to the new node's next pointer. Next up, insertion at the end. To execute this, we have to give new node's address to the last node's next address. Next up, insertion at a specific position. To execute this, we will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now, let's try these operations in a code editor. As you know, a linked list is made up of nodes, so we should start by creating a node. To create a node, we need a class node and we will define its members as public int data and node pointer next. Now we will create a function to insert a new node in front of the list. For this function, as an argument, we will give the reference to the head of the list and integer new data. Now in the definition, we will allocate a node new node equals to now we will put in the data in the new node. We will use arrows to access the data equals to new. Now we will make the next of this new node as head. Now we will move the head to point to the new node. Now we will create another function to insert a node after a specific position. As arguments, we will give it the address to the previous node and and the integer new data. We will first check if the given previous node is null. If it is, we will print given node and not and then we will return the function. Otherwise, Otherwise, we will allocate a new node and then we will enter the new data in that. Now we will make the next of the new node as a next of the previous node. And then we will move the next of the previous nodes as new node. Now we will write a function to insert a node at the end of the list. As an argument, we will give it a node pointer to pointer head and integer new data. We will first allocate a new node we will also create a last node and give it now we will put in the data in the new node since this new node is going to be the last node, so we will make its next as null. Now if the linked list is empty, then we'll make the new node as head. To check that, we will use if star head is equals to null. If it is, then we will do star head equals to new node. Else we will traverse it to the last node while last next not null last is equals to last next. Now we will change the next of the last node as new node. Return. Now we will write a function to print this list. While node is not null, out node arrow data handle and node equals to node. Now we will write the code for the main block. First we will define a head node and mark it as null. Now we will start using those functions to make a linked list. First we will use append function to add 6 in it. Next let's use another function push and add 7 in it. Now we will try to insert 1 at the beginning. So we will use push again. Comma 1. Now let's try to insert 4 at the end. So far the list looks like 1 7 6 4 null. Now let's try to insert 8 after 7. To do that we will use insert after. As argument we will use head next as 7 is present next to the head, comma 8. Now let's try to print this linked list. Cout created linked list print list add return Save. Let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides. Now, let's talk about deletion. First up, deletion at the beginning. To execute this, we have to change first node's next address to null. Next up, deletion at the end. To execute this, we have to change the second last node's address to the null. Next up, deletion at the specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in a code editor. We will start by creating a class node. In this class, we will declare the members as public int data and the node pointer next. Now to insert the data in the node, we will use a function push. As argument, we will give pointer to pointer node head and integer new data. We will allocate a new node we will give this new node the data as new data and new nodes next as head. Now we will write a function to delete the node. As argument, we will give a node pointer to pointer head and int key. Now we will store head in a temp node. And we will create a node prev as null. If head node itself holds the key to be deleted, we will use if temp is not equals to null and temp data is equals to key. Then head equals to temp next. Now we will free the old node. Else we will search for the key to be deleted. Else while temp is not equals to null and temp data is not key, so prev equals to temp and temp will be iterated to its next. If the key is not present in the linked list, then we will just return the function else we will unlink the node from the linked list. And delete. Now we will write print list function to print the list. Its argument will be a node pointer node while a node is not null. Cout less than node data then we will iterate this node using node equals to node next. Now we will move on to the main block. We will start with the empty list node star head equals to null. Now we will add the element to this list. So push ampersand head comma 7. Next push percent head comma 2 push ampersand add comma 5. Next push ampersand add comma 9. Now see out created list print list add. Now we will use delete node function. Delete 2. We will use argument as ampersand head comma 2. Now we will check the linked list. Of 2. Print list let's try and execute this. As we can see, we have deleted the 2 from the linked list. Let's get started with an introduction to W linked list. A W linked list is a linear data structure made up of nodes. This linked list is a bidirectional linked list, that is, we can traverse it in both directions. These nodes consist of three parts. First up, data, reference to the next node, and reference to the previous node. Now let's try to implement the W linked list in the code editor. As you know, a linked list is made up of nodes. So we will start by creating a node. To create a node, we need a class node. Its members should be defined as public. Int data, node pointer, next, and node pointer ref. Now we will write a function to insert a node at the beginning of the W linked list. Void push. The argument will be a node pointer to pointer, add, and int new data. Now let's allocate a node star new node equals new node. Now let's put in the data into the new node. Since we are adding at the beginning, its previous is always null. Now we will link the old list of the new node. Now we will change the previous of the head node to the new node. We will check if head is not null, then head's previous is equals to new node. Now let's move the head to the point to the new node. Now let's write a function to print the given doubly linked list. Its argument will be a node. We will iterate it until the node is not null. Out node data and and node equals to node next. Now let's write a code for the main block. We will start with the empty list. Now we will use a push function to push values in the function. Another push function add comma 3 push function ampersand add comma 5 push function add comma 7. Now out doubly linked list Then we will call the print list function in the W linked list. Let's execute this program. As you can see, we have successfully created our first doubly linked list. Let's get back to our slides. We have now introduced doubly linked list. Now, let's discuss some of the operations we can perform on a doubly linked list. We can perform three operations on a doubly linked list. First, traversal, insertion, and deletion. We can perform a traversal in two ways, a normal traversal and reverse traversal. And we can perform insertion and deletion in three different situations, at the beginning, at the last, and at a specific position after a node. Let's discuss these in detail. First up, normal traversal. We can traverse a doubly linked list using a next pointer starting from head to all the way up to tail node. Reverse traversal. Similar to the normal traversal, we will use previous pointer. We will start from the tail node to go all the way up to head node. Now let's try to traverse the doubly linked list in the code editor. Let's start by creating a class node. We will define its members as public, int data, node pointer, next, and node pointer ref. Now we will write a function to insert a node at the beginning of the doubly linked list. Void push. Its argument will be a node pointer to pointer head and integer new data. Now we will allocate a node star new node new node parenthesis. Now we will put in the data. Since we are adding at the beginning, so its prev is always null. Now we will link the old node to the new node. Now we will change the previous of the head node to the new node. Now we will move the head to the point to the new node. Now we will write a function to traverse the linked list normally. Void traverse node pointer while loop node is not null, therefore cout node data node equals to node next. Now we will write a function to reverse traverse it. Its argument will be a node pointer to pointer head we will create a node tail equals to head while tails next is not null. This loop is enabling us to reach to the tail node so that we can traverse it from backside. Now while loop until tail is not equals to head out tail tail equals to tail ref out tail data handle. This last cout statement is only because we are not traversing till the head pointer. Now let's go to the main block. Let's start with an empty list. Node star head equals to null. Now let us create a linked list to test the function. So we will use push function head comma 2. Another push function ampersand head comma 3. Push head comma 7. Since we are inserting at the beginning, so the actual linked list looks like 7, 5, 3. Now we will print the original linked list first. Cout original traverse head out reverse traversal reverse traversed linked list. Now let's try and execute this program. As you can see, we have traversed it in the normal way as well as the reversed way. Let's get back to our slides. Next up, insertion at the beginning. We will create a node with the previous pointer pointing to a null and the next pointer pointing to the head node. Then we will change the head node's previous pointer to the new node and we will change the new node to the head node. Next up, insertion at the end. We have to give the new node's address to the last node's next pointer and change the new node's previous pointer to the last node. Next up, insertion at a specific position. We will change the previous node's next pointer to the new node and the new node's previous pointer to the previous node and the next pointer to the next node and vice versa. Now let's try these operations in a code editor. We will start by creating a class node public node pointer rev node pointer. Now we will write a function push insert a node at the beginning of the list. Its argument is node pointer to pointer head into new data We will first allocate a new node, node star, new node equals new node parenthesis. Now we will put in the data, node arrow data is equals to new data. Now we will make the next of the new node as head and previous as null. And new node previous is equals to null. Now we will change the previous of the head node to the new node. First we will check if the head node is null. Then star head previous equals to new node. Now I will move the head to the point to the new node. Now let's write another function to insert a node after a specific position. Void insert after argument will be node pointer rev node int to data. We will first check if the given previous node is null. Yes, then we will give it cout a given node can't be null. And we will return to the function. Or else we will allocate a new node equals to new. Now we will put in the data. Now we will make the next of the new node as the next of the previous node. equals to ref node. Now I will make the next of the prev node as new node and make the prev node as the previous of the new node. Now I will change the previous of the new node's next node. If new node next not null, then new node next prev is equals to new node. Now let's write another function. Insert a node at the end of the list. Void append the argument will be a node pointer to pointer head int new data. First we will allocate a new node equals to new parenthesis. Now we will create another node last equals to head now we will put in the data new node data equals to new data. Now since this new node will be the last node, so its next will be null. Head is equals to null. New node rev equals to null and star head is equals to new node. Return. Or else we will traverse till the last node while last next is not null last equals to last next. Now we will make the last node as the previous of the new node. Return. Now we will write a print list function to print this list. The argument is a node pointer node. While node is not null, out node data. Node is equals to node next. Now let's write the main block. We will start with an empty list. We will start by inserting 6, so the linked list becomes 6 null, and ampersand head comma 6. Now we will insert 7 at the beginning, push ampersand head comma 7. Now we will insert 1 at the beginning also. Now we will insert 4 at the end. Till now the linked list looks like 1, 7, 6, 4, null. Now we will insert 8 after 7. So insert after head text comma 8. Now let's print this linked list. Try and execute this. As you can see, we have created our linked list in the correct order. Let's get back to our slide. Next up, deletion. First up, deletion at the beginning. We have to change the first node's next to null and second node's previous to null. Next up, deletion at the end. We have to change the second last node's next pointer to null and delete the previous node to free up the space. Next up, deletion at a specific position. We will change the previous node's next pointer to the next node and next node's previous pointer to the previous node. Now, let's try these operations in a code editor. We will start by creating a class node public int data node pointer next node pointer ref. Now we will write a function to delete a node in a doubly linked list. Void delete node. Its argument as pointer to the head node. Repeat. Its argument as pointer to the head node pointer. And pointer to the node to be deleted. Now we will check the base case condition, that is if head is null or node to be deleted is null, then return now if the node to be deleted is a head node, then head is equals to tell now if next node of the del not null, that is If the node to be deleted is not the last node, then else next previous equals to else previous. Now we will change prev only if node to be deleted is not the first node. So if del prev not equals to null, then del prev next equals to del's next. Finally, we will free the memory occupied by the del. Free del. Now let's write a function to insert a node at the beginning of the doubly linked list. Void pointer to the head node pointer and int new data. We will allocate the node. Now we will put in the data. Since we are adding at the beginning, so prev is always null. Now we will link the old list of the new node. Now we will change the prev of the head node to the new node. Now we will move the head to the point to the new node. Now let's write print list function. Node pointer node while node is not equals to null, out node data node equals to node next. Now let's get started with the main block. We will start with the empty list. Now we will create new nodes. Push %head, comma 2, push ampersand head, comma 4, push ampersand head, comma 6, push ampersand head, comma 8. Now let's print this list. Out original list original list. Now we will call the print list function head. Now we will delete the node from the W linked list. Here we are deleting the first node. Next, let's delete the last node. Now the modified list should look like 4, 8, let's try and print this. Cout modified list head Let's try and execute this. As you can see, we have deleted all the nodes except for 6 and 4. Let's get started with introduction to circular linked list. A circular linked list is a linear data structure made up of nodes. It is like a single linked list except its last node points at the head node. These nodes consist of two parts, data and reference to next pointer. These nodes can be traversed using the next pointer. Now let's try to implement it in the code editor. We will start by creating nodes. To create a node, we need a class node. We will define its members as public, int data, and node pointer next. Now let's write a function to insert a node at the beginning. Void push we will use arguments as a pointer to node pointer head and int data. We will define a node, new node equals to new node parenthesis star head. Now we will put in the data into the new node. Since we are inserting at the beginning of the linked list, that's why this new node's next should be the head pointer. If linked list is not null, then set the next of the last node as head. While temp next is not equals to head, the temp is equals to temp arrow next. Now temp next equals to new node. Else new node next is equals to new node. Star head equals to new node. Now let's write a function to print this linked list. Void print list node star head node star temp equals to head. If head is not equals to null, then do cout temp data temp equals to temp next. Now while temp is not equals to head, this condition is important to stop this loop so that it doesn't go infinitely. Now let's go to the main block. Let's initialize this list as empty. Node star head equals to null. Now let's insert some nodes in this linked list. Push ampersand head comma 2, push ampersand head push ampersand head comma 11, ampersand head comma 5. Now this linked list looks like 5, 11, 9, 2, then it will again go back to 5. Now let's try to print this. Cout circular list head. Now let's try and execute this. As you can see, we have successfully created our first circular linked list. Let's get back to our slide. We have now introduced the circular linked list. Now let's discuss some of the operations we can apply on a circular linked list. We can perform two operations on a circular linked list. First up, insertion. We can perform insertion at three different situations: at the beginning, at the last, and at a specific position after a node. Next up, deletion. We can perform deletion at the three different situations. First up, at the beginning, at the last, and at a specific position after a node. Let's discuss these in detail. First up, insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give new node's address to the last node's reference pointer. Next up, insertion at a specific position. We will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now let's try these operations in a code editor. So far we have implemented a linked list using classes. Now let's try to implement it using structures. We will start by creating a struct node with its element as int data and struct node next. Now we will write a function which can only insert a node to an empty list. Struct node star add empty. Struct node star last comma int new data. Now since this function is only for the empty list, so we will have to check if the linked list is empty or not. If last is not equals to null, then we will return last. Now let's create a node dynamically. Struct node start temp equals to struct node star malloc size of struct node. We will copy this statement because we will need it in the future functions. We will assign the data to this new node. Temp data is equals to new data. Last is equals to temp. Now we will create the link. To do that, we will use last next is equals to last. Since we are in an empty list, so the first node will always point to itself. Return struct node start. We are creating a function to insert at the beginning of the linked list. Struct node star add begin as argument. We will use struct node comma int data. If last is equals to null, then we will return add empty last comma data. Now we will create a node dynamically. I've already copied this statement for the ease. Now we will put in the data. Data is equals to data temp next is equals to last next last next is equals to return last. Now we will write a function to insert a node at the end. Struct node star add and struct node star last int if last equals to null, then return add empty last comma data. Now we will dynamically create a node and put in the data. Temp data is equals to data temp next is equals to last next. Now last next is equals to temp and last equals to temp. Return. Now we will write a function to insert a node after a specific node. So struct node star add after struct node star last comma int data int item. This item is a node after which we have to insert the node. If last equals to null, then return null. Struct node star temp comma star p is equals to last next. Now do if if equals to item temp equals to we will dynamically create a node here. Temp is equals to struct node star malloc size of struct node. Now we will put in the data. So temp data is equals to data temp next is equals to next. Now p next is equals to temp. If p is equals to last, then last is equals to temp. Return last. Equals to p next. While not equals to last next. Cout item not present in the list. Return last. Now we will write a function to print this list. Void print list struct node star last struct node star p. Now if last is equals to null, then cout list is empty and return. Else, we will point to the first node of the list. So P is equals to last next. To traverse the list, we will use do while loop. So do cout data is equals to P next. While P is not equals to last next. Now let's write a code for the main block. We will start with an empty list struct node star last equals to null. Now last is equals to add empty last comma 6. Last equals to add begin last comma 4. Last equals to add begin last comma 2. Last equals to add end last comma 12. Last equals to add after last comma 10 comma 4. Print list. Let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides.
Now, let's talk about deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to null to execute this. Next up, deletion at a specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in the code editor.
Let's get started with creating a node. To create a node, we need a class node. We will declare its members as public int data node pointer next. Now we will write a function to insert a node at the beginning of the list, void push a pointer to the node pointer head and int new data. Now let's create a node and make head as next of it. Node star new node equals to new node parenthesis. Let's put in the data new node data is equals to new data and new node next is equals to head. If linked list is not null, then set the next of the last node as the first node. If star head is not null, then we will find the node before head and update next to it. So node star temp is equals to star head, while temp next is not equals to head, temp is equals to temp next. Now temp next equals to new node. Else new node next is equals to new node and star head is equals to new node. Now let's write a function to delete a given node from the list. So void delete node. Its argument is a pointer to the node pointer head and int key. Now if linked list is empty, then we will simply return it. If star head equals to null, then return. Otherwise, if head head data is equals to key and head next equals to head then free head head is equals to null. Return. Now node last is equals to star head comma star d. Now if head is to be deleted, then star head data is equals to key, then while last next not equals to star head, then last is equals to last next. Now we will point the last node to the second node of the list. Now we will free this head star head equals to last next. Now if either the node to be deleted is not found or the end of the list is not reached, then while last next is not equals to head and last next data is not equals to key, then last equals to last. If node to be deleted was found, then if last next data is equals to key, then d is equals to last next and last next is equals to d's next. Now we will free d. or else cout no such key found. Now let's write a function to print this list. Void print list node star head node star temp is equals to head if head not null, then do cout temp data temp is equals to temp next while temp is not equals to head. Cout now let's write a code for the main block. We will start by empty list. So node star head equals to null. Now we will push ampersand head 2 push ampersand head comma 5 push ampersand head comma 7 push ampersand head comma 8 and push ampersand head comma 10. Now we will print the list before any deletion operation. Cout list before deletion print list Add. Now let's delete ampersand add. Let's delete 7. Cout list. After deletion, print list. Add. Let's execute this. As you can see, our deletion function is working perfectly.
In this particular session, we will discuss the differences between the two major data structures that are the arrays and linked lists. So at first, what exactly is an array? So an array is a linear data structure that stores homogeneous data elements in a continuous form. So homogeneous in the sense, you will be able to store only one single data type of elements in an array. For example, consider that you have declared an array and you wanted to store some elements in the array. So you can declare a data type first, after that the name of the array, and if you declared that the array should store integer data type, then you can only store integer elements in that particular data type. You cannot store any other data type like float or character. That is the meaning of this particular definition. And it stores the elements in a continuous order, that is in the adjacent format, as you can see in the example here, 10, 20, 30, 40, and which are located in the adjacent locations, that is 0, 1, 2, and 3. Now let us understand what exactly is a linked list. So similar to array, even a linked list is a linear data structure. But the only difference is it is a dynamic data structure. Here, you can increase or decrease the size of the linked list in runtime. The only difference is here the memory locations are not adjacent to each other, but they are taken from the memory heap. So there is a huge memory chunk. Out of that, the linked list will borrow some of the memory locations, and one after the other, the memory nodes will be interconnected using pointers. So that was the difference between array and linked list. And similar to arrays, even the linked list store homogeneous type of elements. That is, if you declare a linked list of float data type, then you can only store float data type in it. You cannot store any other different data type like character or string. Now followed by that, let us understand the types of arrays. So basically we have three different types of arrays. Those are the one-dimensional arrays, and inside multi-dimensional arrays we find two more types. Those are the two-dimensional arrays and three-dimensional arrays. Now one-dimensional arrays will be having only one subscript, that is, they'll be having only one single row. Whereas in the two-dimensional arrays we will be having two subscripts, that is, it will be having rows and columns. And in the three-dimensional arrays it will be having three subscripts, that is, the row, column, and the block address. Now, followed by the types of arrays, we will understand the types of linked lists. So similar to arrays, even linked lists are divided into three types. They are singly linked list, doubly linked list, and circular linked list. The difference between them is a singly linked list will have two parts, that is the node address and node element. In this particular segment, the element will be stored, and in this particular second segment, the address that points to the next node will be saved. And similarly in the circular linked list, the only difference between the singly linked list and the circular linked list is at the end of the singly linked list, you can see a null pointer which indicates the end of the linked list. But in circular linked list, the address will not be null. Instead, it will point back to the head node. That is what which makes it as a circular typed singly linked list or a circular linked list. When it comes to the third type, that is the doubly linked list, we can see there are two address locations. The first starting node will have null as its first address location, then we'll store the element, and the second address location will point to the next node. And you can see in the second node will have element, and the first address location will point to the previous node, and the second address location will point to the next node. And at the end, the second address location will be pointed as null, which indicates as the end of the linked list. Now that we know the types of linked list and arrays, we will look into the fundamental differences between arrays and linked lists. So the first fundamental differences between the arrays and linked list is the array element can be accessed randomly using just the index values. But whereas random access is not possible in linked list. If you want to access any element in linked list, you need to perform the traverse operation sequentially. The second difference between the both is array is static, which means memory size is fixed, which cannot be changed in runtime. But whereas in the linked list, the memory is dynamic, which means you can either shrink or expand the memory in runtime according to your requirements. Followed by that, the next difference is each element in array is independent in nature. That is, you can access any element just by giving the index location. Whereas in linked list, the elements are interdependent on each other. Whenever you want to access a specific element, you need to go through the other elements or traverse through the other elements. Next one is the array takes more time in operations like insertion and deletion, whereas linked list takes less time to perform the operations of insertion and deletion. Followed by that, the next difference is accessing any element is faster in array as random access is possible, and the array data structure just by using its index values. But whereas accessing an element in linked list is slow because we know that we need to traverse through all the node elements to access a particular element. Now the next difference is, in case of an array, memory allocation is done in compile time. Whereas in linked list, the memory allocation is done during the runtime. Memory utilization is inefficient in an array as it is allocated as in static and it is allocated during the compile time. In case of linked list, the memory utilization is very efficient as the memory is allocated during the runtime.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
What is a stack? So basically, stack is a linear data structure just like arrays and linked lists. The only difference is that it follows a specific order when an operation is implemented on it. So what is the specific order that it follows? That is LIFO, last in, first out, or FILO, first in, last out. In the next parts, we will understand this order in a much better way. All operations can be done only at the one end of the stack, that is on the top. Now we will discuss much about that in the operations part of the stack. Now let us understand the first fundamental, that is the representation of stack. That is, how do you represent a stack normally? So a stack can be represented using two different methods, that is using an array or using a linked list. So in an array, we will be using the continuous memory. And in stack, we will be using a non-continuous memory, and the stack will behave like a dynamic stack or a dynamic data structure. Now the first method, that is the array method. So in this method, an array is used to represent the stack. As you can see in the image below, we have a stack. So the name of the stack is stack itself, and you can see two more things here. That is top is equals to 2 and max is 4. So the max is the value of the array or the length of the array, the maximum length of the array, and top is the position where the last element of the stack is present. Here in this case, 56 is the last element in the stack, and top is inclined or it is addressing to that particular address, that is 2. And now let us discuss about the linked list representation of stack. So in this method, a dynamic data structure, that is a linked list, is used to represent the stack. This representation leads to a dynamic stack. It does not need to define the maximum number of elements present in the stack. Remember, in arrays, we had to define the max value. In the previous example, we had the max value as 5, but in here, you need not to assign the max value as the stack itself is dynamic. The pointers links are used to store the address of the upcoming nodes, and the variable used in this method is top. So the top is holding the address of the topmost element in the linked list representing the stack. Now moving ahead, we shall understand the basic operations on stack. Now here, we will understand the previously discussed definition, that is push, pull, etc. in a much better way. So the basic operations on a stack are push, pop or pull, and peek. Now let us discuss each one of them in a detailed way. The first one is push operation. So the push operation is the mechanism of inserting a new element into the stack. As you can see, we are trying to insert the elements from the top. So the push operation basically involves the following steps. Check if the stack is either full or not. So basically, whenever you're trying to insert an element into the stack, you need to make sure that the stack is empty or it has some space. If it is full, you cannot insert an element into the stack. Step 2. If the stack is full, produce an error and exit. That's what I was talking about. Now the step 3. If the stack is not full, increment the top by 1. That is, when you're inserting an element, then you need to update the top value. For example, in the previous slide, when we had the array representation of a stack, we had the top value as 2. So if you try to include an element into the stack, then you need to update the top value from 2 to 3. That is incremented by 1. Now the fourth step, add data elements to the stack where the top is pointing. And finally, success. The push operation has been successful. So this is how you insert or push an element into the stack. Now followed by push operation, we have pop or pull. So the pop operation is a mechanism of eliminating or deleting or removing one data element from the existing stack. So we shall understand the pop operation in a much more detailed way. The operation involves checking the stack is empty or not. If in case the stack is not empty, then you can carry forward the pop operation. But in case if the stack is empty, then you have to provide an exit status and exit the control and leave the stack. So if the stack is not empty, approach the data element at the top, that is at the top position. For example, in the previous array example, remember, right, we had the top position pointing towards 2. So you need to take the control to the top position and pick out the element and pop it. And finally, decrease the top by 1. So when you eliminate the top element, then the top value from 2 will be decremented to 1. So this is how the pop operation is carried over on a stack. Next one is the peek operation. The peek operation involves returning the topmost data element from the stack without moving it. So here you can see the top is pointing to the element number 4 and you're peeking the element number 4 and you're not removing it from the stack. You're just returning the topmost data element. You're passing the value of the top element. So to understand the push, pop and peek operations on stack in a much more better way, let's carry out a practical example. Now we are on the practical mode and here you can see on my screen we have the code example for the stack. Now first we'll be checking if the stack is empty as per the steps mentioned in the previous discussion. We will check if the stack is empty or not. If it is empty, then we will return, else we will continue. And again another step, we also check if the stack is full. If the stack is full, we will exit, else we will continue with the operation, whatever it is, peek, pop or push. And here we have an example for the peek operation that we discussed previously, and followed by that we have a pop operation. We are trying to exclude an element from the stack, and another one we have the push operation where we'll be trying to push the elements into the stack. So these are the three functions for push, pop and peek. Now we'll try to push in the elements and also pop and try to involve some functions on it or run some operations on the stack. Now let's run this code and see the output. So you can see that the code has successfully executed and we have the statements here. The first one says the stack is not full, that is false, and stack is empty, that is true, right? And after that you can see that the elements which we tried to push into the stack, that is 11, 76, 71, 15 and 66 are been pushed into the stack. And if you clearly observe it, we have the element 11 in the bottom, 76 upon that, 71 upon that, and 15 and last 66. So the order is first in, last out. That is, the first element was pushed first, and when you are trying to eliminate the elements from the stack, then you will first pick out 66, followed by that you will pick out 15, followed by that you will pick out 71 and so on. So this is the rule what stack follows. Now I hope I made myself clear with the example. Now we shall continue with the applications of stack. So these are the few applications of stack. The first one is expression conversion. So you can see we have the infix notation, prefix notation and postfix notation. So the infix notation is no rocket science. There is only one thing here to learn, that is we have two operands A and B, and we have one operator, that is the addition operator, in between those two operands. And when you use the prefix notation, you will have the operator located at the first place, then you will have the operands followed by it. And in the postfix one, you will have the operands first, and followed by the operands you will have the operator. So basically all the infix, prefix and postfix notations give out the same results, but the only difference is the representation of those operands and operators. Now let us understand this in a much more detailed way. So conversion of expression from one form to another form is the main application of stack. So we have the first one, that is infix to prefix and infix to postfix. Now let us see an example. Here you have 1 plus 2 star 3 plus 4. So this is the normal infix notation. And when you try to present the same expression in the form of prefix notation, so this will be the result, and this is the result for postfix. The next one, prefix to postfix and prefix to infix. And this is the way you write the prefix notation, and if you want to convert that to infix, this is how you can write it, and this happens to be the result of postfix notation. And finally, postfix to prefix, postfix to infix, and these are the results. Now followed by expression evaluation, the next important application of stack is checking parentheses. And you can see if the parenthesis is set properly, the expression gets evaluated. If not, it will not be evaluated. Now the last one, memory management and function call. The very useful thing of using a stack is the memory will not be allocated to your stack elements unless the function is called. Here you can see it is the main function, and these are the elements that you wanted to declare into your stack. And unless you make a function call, the elements will not be declared their memory, or the elements will not get the memory allocated for them. Now another good application of stack is the backtracking problem, or the n-queen problem. The n-queen problem is an example of backtracking problem. The n-queen solution to this problem is to position the queen in such a way that the opponent queen cannot attack your queen. Now another example is string reversal. You can see on my screen we have a string that is A, B, C, D and E. Now using stacks you can reverse this, right? So you're basically eliminating an element and relocating it to the first place. And finally, after reversing your string, this will be your result, A, B, C, D and E. Followed by that we have conversion evaluation. So stack is used to evaluating the expression as shown in the example. Since parenthesis has the highest precedence, 5 plus 4 gets evaluated first, and it will result in 9. Then multiplication and division have the same precedence. Now the associativity comes into picture. So the associativity is always from left to right. So first 4 into 9 will be executed, which will result in 36, and then 32 divided by 4, which will give us 8. Now we have 36 minus 8, which will give us an answer that is 26. Now the last application is the Tower of Hanoi. So the Tower of Hanoi is a mathematical puzzle consisting of 3 rods and n disks. This puzzle consists of some rules. The first rule states that one disk can move only at a time. The second rule is that the disk can only be moved when it is at the uppermost position on the stack. The third one, no disk is allowed to place on the top of the smaller disk. So this is how the Tower of Hanoi works. What is a stack? So a stack is a linear data structure that follows FIFO or first in, first out principle. All the operations on the stack are done only from one end, that is the top. So you can see this image here, and this particular image of books can be considered as stack. And you can see that the addition or elimination of elements, that is books in this particular case, is happening only through the top section. Now we will understand what are the basic operations that can be performed on a stack. So the basic operations that can be performed on a stack are push, pop, and peek. So this particular image on the right side will help you understand what exactly is push, pop, and peek. As we discussed, the elements will be added into the stack from the top. So when you add an element from the outside into the stack, it will be pushed from the top. That is the push operation. And if you want to eliminate an element from the stack, it will be eliminated from the top. That is the pop operation. Apart from these two, that is push and pop, we have another operation that is called as peek. The main intention of peek is just to see the element which is on the topmost part of the stack. It will just retrieve the element from the top. It will not pop it, or it will not push any other element onto the top. It will just copy and it will just print what is present on the top. So these are the main operations, that is push, pop, and peek. Now let us see how to implement this stack using array. So implementation of stack data structure can be done in two ways, that is array and linked list. Now in this particular session, we will learn how to implement stack using array data structure. Now without further ado, let's get started with the implementation of stack. So we will be performing push operation, that is inserting a new element into the stack. Now followed by that, we will be performing the pop operation onto the stack, that is eliminating or deleting an element from the top position of the stack. And followed by that, the last operation, that is the peek operation, where we will be just retrieving the topmost element from the stack without removing that element from the stack or without adding any new element to the stack. Now that we have a detailed understanding of what are the basic operations that can be applied onto the stack, let's get started with the practical implementation. Now you can see that on my screen we have the basic fundamental operations onto stack, that are the push and pop. Now without further ado, let's get started with running this code. Don't worry about the code. This particular code will be present in the description box below, or if you need it, you can always write down to us in the comment section below and we will have it sent to your mail ID so that you can have a better understanding of the code and try to execute the code in your local system. Now let's run the code and see the output. As you can see, the code got successfully executed and the topmost element is A and the topmost element is B after the element is being popped away. And it says that the element B was popped out, and after that the topmost element was A, and after that the element A was also popped out, and now the top is pointing to -1, which means to say that the stack is empty. In this session, we will learn about linked list implementation using stack. So first up, what exactly is a linked list? So linked list is a dynamic data structure. It allocates memory dynamically. The nodes are maintained in a non-continuous memory. That is, in linked list we have nodes. So each and every node is connected via a pointer which points to the address of the next node. Each node contains next pointer, that is the next pointer's address, which keeps the reference to the next node, and it also has another section which stores the data. the topmost node always contains null in its address, and this is how a linked list looks like. So this is the top, which is the beginning position of the linked list, and this is the address of the first location, and this is the next node, this is the following node, then this is the last node, and this points back to the head node. So this is how you can implement a stack like data structure using linked list. You can see that we can perform stack like operation, that is the elements are located one above the other and the top is pointing to the head node. Now let us go through the implementation of stack using linked list. First, we will go through traversing of stack using linked list. So displaying each node of the linked list representing stack is termed as traversing. Copy the head pointer to the temporary pointer and then move temporary node through all the nodes and display values of each node. So you can see the animation here will explain you how the traversal goes through the linked list in real time. Now another linked list implementation of stack is the push operation. So adding a new node to the top of the stack is termed as push operation. Generally, in stack we have three operations, that is push, pop, and peek. So one of the operation is push, where you add an element into the stack. In the same way, using linked list, you can add a new node to the stack and point it as the top of the stack or the first element, which represents the top in terms of stack. Now create a node first and allocate a new memory to it. If the list is empty and node consists of data and null is the address, it will be inserted as the first node. If there is some node already existing, then add a new node at the beginning to avoid violations. So the following animation will help you understand how we add a new element or the top element to the stack using linked lists. Now followed by the push operation, we have the pop operation. So now let us go through the pop operation. Removing a node from the top of the stack is termed as pop operation. In the same way, we will be eliminating the first node from the linked list, which is termed as top. Underflow condition may occur when you try to remove the node if the stack is already empty. In stack, node can be removed from one end only. Therefore, the value stored in the head pointer must be deleted and the node must be freed. Followed by the pop operation, we have the peek operation. Retrieving the topmost node of the linked list representing stack without removing the linked list node from the top of the stack is termed as peek operation. Generally, when you're using a stack data structure, just retrieving the value of the top node is called as peek operation. You're not going to eliminate or you're not going to add a new element to the top. You're just going to copy the element or you're just going to retrieve the element which is pointed as top. This operation is called as peek. Now, in the linked list, you can also perform this operation of peek. Now, with the theory discussed, let us execute a practical program based on stack implementation using linked list. Now on my screen, you can see a code example using which we will implement stack using a linked list. Now here we have the pop operation, push operation, and top, and then the main function. Don't worry about the code. This particular code snippet will be attached in the description box below, or you can also request us and we will have it sent to your mail ID and you can understand the code and try executing in your local system. Now without further ado, let's directly run the code. So there you go. The code got successfully compiled and we have tried to add some elements into the stack, that is A, B, C. And C is being the topmost element of the stack, and that element has got popped, and followed by that the element on the top currently after C being popped out is B, and the node element B got popped again, and the only element which was present in the stack is A, and that element is also popped out after performing the pop operation, and now currently the stack is empty. You can see that we have tried to push the elements A, B, C, and also we tried to pop the elements A, B, C.
Let's get started with Introduction to Queue. You know that all of us depend on messaging applications like WhatsApp, Facebook Messenger, Instagram chats to communicate with our friends and family members. And while using them, you must have observed that the person you are trying to communicate with receives messages in the same order as you have sent them. Now the question that arises here is, how is this happening? How are these applications maintaining the order of these text messages? And the solution to these questions bring us to queue. Basically, in these applications, a queue is maintained for each user, containing the messages to be delivered to the user. When the user connects to the network, all the text messages in the queue gets delivered, and once the messages are delivered, empty queues get deleted. This example clearly illustrates the importance of data structures. So let's dive further and understand the structure of the queue in depth. But before doing that, let's look at a real-life example of queues to understand it more clearly. The most common and relevant example of a queue is a movie ticket counter. In the movie ticket counter, you must have observed that both of its ends remain open. Also, these ends are fixed with the help of barricades, and that is why no one can enter in between these ticket lines. Additionally, the person who enters first receives a ticket first, and the person who enters last will obviously get served at last. Queues in data structure resembles all these properties of a movie ticket counter, which makes them better at creating virtual first-come, first-served systems. Basically, they are defined as a linear collection of different data types that allow insertion at one end and deletion at another. Unlike any other data structure, the queue ends remain open, allowing it to have different functionalities at both ends. The end at which insertion takes place is called rear, and the end at which deletion takes place is known as front. Furthermore, there are two approaches to consider the structure of the queue, and both of them depend on the approach of the programmer. That means, being a programmer, if you consider the left end as front, then your rear node will be at right end. Otherwise, if you consider the left end as rear, then the right end will be your queue's front node. Unlike arrays and linked lists, elements in the queue cannot be operated from their respective locations. Here, they can only be operated from the front or rear position. Moving on, let's discuss the operations in queue data structures one by one. The first operation is enqueue. It is used to store the elements in the queue. Next up is dequeue. This operation is used for removing them. Further, we have isFull and isNull operations. IsFull function scrutinizes if the queue is full or not, and the isNull operation evaluates if the queue is empty. We also have a peek operation that helps you get the element from the front of the queue without removing it. Let's now understand how these operations work with the help of the following examples. Here we will look at enqueue5, enqueue1, enqueue-2, then isFull, then dequeue, peek, and isNull. But before explaining these operations, it's essential that we initialize the queue data structure by assigning some random size to it. For example, int queue of 3. By this declaration, we are assigning only 3 spaces for insertion in queue. Also, at this phase, there is no element in the queue as it's empty. So both the front node and rear node will point to the same location with null memory space in the storage system. Let's consider that null index to be -1 for ease of our convention. Now the first operation on our list is enqueue of 5. As we discussed previously, enqueue operation is nothing but the insertion of data into a queue data structure. It begins with checking if the queue is full or not. If the queue is full, then the previously assigned memory is completely filled with data elements. So insertion would not be possible. This is also known as overflow error in terms of programming. But as our queue is empty, so the insertion can be performed here. For that, we have to increment the rear pointer to index 0 from index -1. And once we do that, the data element 5 will be added to the queue. Also, for front insertion, both front and rear will point to the same location as there is only one element present in this queue. Let's insert 2 more elements into this queue with the operations enqueue1 and enqueue-2. For that, we have to increment the rear pointer to the next index, which will be 1. Now, as the pointer is incremented, so the data will be entered into this position. Next up is enqueue-2. Again, we have to follow the same process of incrementing the rear pointer. We will increment the rear pointer to point towards the next index, that is index 2, and hence the data element with value -2 will be entered here. The next operation on our list is isFull. In this operation, if the rear pointer points to the max size, then the queue is considered to be full as there is no space left for insertion. In our case, the max size of our queue is 12 bytes. Additionally, we are considering to enter only 3 integer elements. And one integer data element takes 4 bytes of the memory space. That means 3 integer elements will take 12 bytes. Hence, this function will prompt queue is full on the screen. Now we will discuss the dequeue operation. If we want to access data from a queue, we have to perform 2 subtasks. The first one is access the data where the front is pointing, and another is to remove the data after access. And this complete process is called as dequeue operation. The first step of this operation is to check if the queue is empty. If the queue is empty, then there is no element available for deletion. This is a case of underflow error. But as our queue is not empty, we can proceed with the next steps. We will be accessing data from the front node, and later we will be incrementing the front pointer in order to remove the link to the previous node so that the data gets removed. Now, front will point to the index 1. Thus, the data value 5 will be removed from the queue and will also be prompted on the screen. Therefore, this function comes with an integer return type. Next up is peek operation. In this operation, element at the front node will be accessed without deleting it. The algorithm for this operation begins with checking if the queue is empty or not. If the queue is not empty, then data at the front node will be accessed with temporary variable and printed on the screen. Advancing further, let's perform 2 more dequeue operations here. First is dequeue of 1 and another one is dequeue of -2. The data at a front node will be accessed primarily, and the front pointer will be incremented to point to the next data element. When we do the pointer incrementation, the link to the previous node gets removed, which results in data deletion. Similarly, we will perform a dequeue of -2 operation here. Now, the front will be pointed to null memory space as there is no element left in our queue, and the data -2 will be removed. The last operation on our list is empty. This function checks if the queue is empty or not. In the previous procedure, we mentioned that if the front points to the null memory space, then the queue is empty. And in our case, the front is already pointing to -1. So the output of this function will be queue is empty. This is all about operations in the queue. I hope that you all are clear with these operations. Next, we will discuss different types of queues and their structures at a glance. Basically, there are 4 types of queues: linear queue, circular queue, priority queue, and double-ended queue. The structure which we have discussed till this time is that of a linear queue, so now we will move on to circular queue. The circular queue is almost similar to the linear queue, except that the last node of this queue is connected to the first. It is also known as ring buffer as all the ends are connected to another end. Additionally, this circular queue is a better version of the linear queue as it removes the drawback of insertion in the linear queue. The empty space available in a circular queue can be filled with the new element by simply incrementing the value of the rare position. We will learn about this in detail in our further sessions. A priority queue is another special type of queue data structure in which each element has some priority assigned with it. Based on the priority of each element, the elements are arranged in a priority queue. If the elements occur with the same priority, then they are served according to the first in, first out principle. In the priority queue, the insertion occurs based on the arrival, while the deletion occurs based on the priority. The above figure shows that the highest priority element comes first, and the elements of the same priority are arranged based on the first in, first out structure. The last type of queue is dequeue. Dequeue is a linear data structure in which the insertion and deletion operations are performed from both the ends. We can say that dequeue is a generalized version of the queue. Dequeue can be used as stack as well as queue as it allows the insertion and deletion operations on both the ends. If the insertion takes place at one end and deletion at another, then that dequeue is known as a linear queue. And if both addition and deletion are performed at a single end, then that dequeue is called stack. Advancing further, let's discuss some applications of queues to gauge an insight into the importance of queues. The queue data structure is used in computers, printers, and applications to utilize the benefits of the first come, first served technique. In computers, whenever you work on documents or PPTs, you must have observed that whichever key you press on the keyboard appears in the exact same order on the screen. But when your processor is too busy with other tasks, you might notice that the keys you press appear on the screen with some delay after you press them. Basically, those keys are stored in queue, and when the processor becomes free, it processes in the order the keys are pressed. That means the key pressed first will be written in a Word document first. So this is how computers use a queue to eliminate deadlocks when multiple processes are in a ready state. Next up is printers. A queue data structure is used in printers to maintain the order of pages while printing. That means the pages are stored in a queue in the order that you want to print them, and once the page is removed from an ordered queue, it gets printed. Another most common application of queue data structure is their usage in web or mobile apps. Applications like Domino's, Swiggy uses a queue for maintaining food order status. If you place an order from an online portal, your order ID enters the queue. And once the previous orders before your order ID gets catered, then your order will be catered as well. From these examples, we can clearly say that queues are used whenever there is a need for an FCFS strategy in software development. So whenever you work on projects that need a first-come, first-serve approach, then remember that you have to implement a queue data structure to complete it successfully. Finally, let's have a look at some key takeaways that we discussed in this session. We started this session by examining the structure of the queue. We learned that the queue is a linear data structure. After that, we talked about different operations of queues in which we learned enqueue and dequeue are responsible for data manipulation in a queue. Later, we discussed different types of queues as well. Finally, we discovered some applications of queues and how they fulfill the need of FCFS systems. We have also made it clear that queues can handle multiple data types as well. Having said that, let's dive deep into the strategy to implement queue data structure. Until now, we have understood that queue is a special kind of list with some restrictions on insertion and deletion. And there are two approaches to deal with queue implementation. The first one is array-based and another one is linked list-based. In this session, we are going to focus on array-based implementation. Initially, let's say we want to create a queue of integer elements. For that purpose, firstly, it is essential to declare an array of random spaces. Let's take 100 as the size of our array. That means our array can have a maximum of 100 integer elements. The declaration of an array is made with this line of code, int q100, where int represents integer data type and q is the name of our array, and 100 is its size. The array that we just initialized is going to store our queue. By that, what I mean is at any random index of an array queue is going to start with two marked ends, front and rear. In this array, I'm showing front of the queue towards the left and rear towards the right. For making those end nodes, we need to initialize two pointers, front and rear. At this moment, as our queue is empty, so both of those pointers should point towards -1. So initialization of these pointers should be done as int front is equal to -1 and int rear is equal to -1. When the insertion or deletion happens in queues, these pointers will be either incremented or decremented, so they are an essential part of this queue implementation process. Now you must be clear with the array and pointers declaration part. So let's dive further and formulate code for queue implementation using a one-dimensional array in C++. It is essential to include header files into our source file as we cannot access standard C++ functionalities without them. That is why here we are going to load IOStream and standard input-output files along with using namespace std. Once this is done, we will initialize our array along with front and rear pointers. Remember, we always have to declare the size of an array before compilation. That means we cannot update the size of an array at runtime. This scenario is the biggest limitation of queue implementation using arrays. Having said that, let's proceed with pointers declaration. Now we are done with the initialization process. We will now work on implementation of queue functionalities. Let's first work out supportive queue functions like isNull, isFull, and peak. isNull function validates if the queue is empty. And as per our previous discussion, when both front and rear points to -1, then the queue is considered to be empty. So the condition to determine if queue is empty will be if rear is equal to -1 and front is equal to -1, it will return queue is empty. If the queue does not satisfy the previous condition, then it is not empty. So by using the else condition, we can display the queue is not empty. Next up is isFull function. This function validates if the queue is full, and we can clearly say that if the rear pointer is equal to the max size of the queue, then our queue is going to be completely full. Next is peak. The peak function extracts the element where the front pointer is pointing without removing it from the queue. For this functionality to work, our queue must contain data elements in it. What I mean is our queue should not be empty. If our queue is not empty, then data at the front node can be accessed. This is how we implement supportive queue functions. Let's immediately dive into the development of main queue operations, enqueue and dequeue. For enqueue operation, if the queue is full, then our function should prompt an overflow error. For that to happen, we have to put this condition. If the front pointer is pointing to -1, then we have to increment the front pointer to 0 manually. Otherwise, it can be incremented by rear ++. After pointer incrementation, we have to ask for a data element to enter into the queue. Once the data is given, it should be inserted at the position where the rear is pointing now. Finally, let's code the final main queue operation called as dequeue. If the queue is empty, then there is no element for deletion, so it should prompt an underflow error on screen. Also, if there is only one element left inside queue, then both pointers should again be pointed towards -1. For that, let's write another condition here. If both the previously mentioned conditions are false, then deletion of an element can be achieved by just pointer incrementation. We have implemented all the queue functionalities here, but we haven't implemented a function that can show us how our queue looks. So for that, let's implement one more function with the name display. This function should prompt the elements of the queue on the screen. Elements will only be printed if the queue is not empty. Hence, we have to check for the emptiness of the queue first. Finally, we are done with the hard part. So let's arrive at the main function to contemplate these operations in order to visualize outputs. We are going to use a switch case to take a user command. Thus, not to waste your time on this, let me just get done with this block ASAP. That's all, we are done with the queue implementation using arrays. Let's just examine if our code works fine or not by compiling it. This program should return a console that asks the user to give commands for performing different operations. So as you can see on your screens, if I input 1, I can perform insertion in a queue. Let's perform some insertions now. We will insert 4 elements, first 3. Then 21, next 78, and finally 12. After inserting these elements, we will print the state of the queue using case 3. Now let's also check the dequeue function. If we perform a dequeue operation, then 3 should be removed from the queue. Let's check if it is removed using the display function. And yes, our code works just fine. Now if you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. Additionally, you can also try to run it on your local system to have a better understanding of the concept.
When we discussed the implementation of queue using arrays, we discussed the limitation of fixed size. According to that limitation, an array will always have a fixed size and it should be declared before the compilation of program. Furthermore, once all the positions in an array are taken or it is exhausted, then we only have two options. We can either deny insertion by saying that the queue is full and we cannot insert anything now. Or what we can do is we can create a new larger array and copy elements from the previous array to the new larger array. The time complexity for this copy operation will be proportional to the number of elements inside field array. In other words, we can say that the time complexity of this copy operation will be big O of n. But again, as we are giving random larger size to the array, there is a possibility of massive memory loss. Like right now in this array, 70% of the memory is unused, and the memory is a crucial resource that we should always be protecting. It's not that some amount of unused memory will be a real problem in today's modern day computer, but it's just that while designing solutions and algorithms, we should always analyze and understand these implications regarding memory. Along with this memory wastage, there exists another sort of memory management issue that occurs while utilizing an array to implement a queue data structure. The space of an array which is used to store elements can never be reused to store the queue elements, because items can only be inserted from the front end and the front end's value may be so high at that time the space before the pointer will be lost for eternity. Let's have a look at an example to understand this drawback more clearly. In this example of array representation of queue, a queue of size 10 having 5 elements is shown. The value of the front pointer is 5. Therefore, we cannot reinsert values in the place of already deleted elements before the position of front. That means the space of the array before front pointer can never be reused for storage purpose. These drawbacks represents the need for a more appropriate method to implement queues. And by using a proper dynamic data structure like linked list, these drawbacks can be easily removed. On that note, let's discuss about the representation of queue using a linked list. A linked list, as we know, is a collection of data elements that we call nodes. These nodes are stored at non-contiguous locations in memory. Further, each node contains two fields, one to store data and another to store the address of next field or the reference to the next node. Let's assume that the node in this figure are at addresses 200, 400 and 500 respectively. I have filled these addresses in the address field as well. The identity of the linked list that we always keep with us is address of the head node. We often name a pointer or reference variable at which we store the address as head. So now we are saying that we want to use a linked list to implement queue data structure. And the basic definition of queue conveys that a queue is a linear data structure in which insertion is performed at the rear node and deletion at the front node. It's really effortless to enforce this property of a queue in linked list. We can simply pick one side of a linked list for insertion and another side for deletion. If the head node is considered to be front, then the tail node will be the rear. Otherwise, if the head node is deemed to be the rear, then the tail node will be the front end. Whatever side we are picking for whatever operation, we just need to make sure one thing, and that thing is the operations that we are carrying out must take a constant time, or in other words, their time complexity should be big of 1. I hope that you guys are clear with the representation of a linked list as a queue data structure. Now moving forward, we will discuss about its implementation. But before that, let's have a look at the time complexity management challenge which occurs in queue implementation of a linked list. In the case of linked list, the cost for insertion or removal from the head side is big O of 1, but the cost for insertion or removal from the tail side is big O of n. So here is the deal. In a standard implementation of queue using linked list, if we insert element at one side and remove them from other side, then one of these operation NQ or DQ, depending on how we are picking this side, will cost us big O of n. But the requirement that we have specified before for queue implementation suggests that both these operations must take a constant time. So we'll definitely need to do something to ensure that both NQ and DQ operations take constant time. Let's call this side front and this side rear. So I want to NQ a node from the tail side and I want to perform a DQ at the head side. We are good for DQ operation because removal from the front will take a constant time, but insertion or NQ operation will be costing us big O of n. Let's first see why insertion at the tail will be costlier, and then maybe we can try to do something. To insert an element at the rear end, what we will have to do is, first we'll have to create a node. Let's say I got this node at address 350 and the integer that I want to enqueue is 7. The address part of this node can be set as null. Now we have to build a link with this created new node, and to do that, first we'll set the address part of the last node as the address part of this newly created node. But the only identity that we always keep with us in case of linked list is address part of head node. So to get appointed to any other node, we need to start at head. That is why first we'll create a pointer variable temp and we'll initially set it to head node. And now using this temp pointer, we'll traverse to the end of our linked list, that is the tail node. And here, using this pointer temp, we can write the address part of the newly created node at the previous tail node to build this new link. This traversal of pointer from head to tail is taking all the time for insertion. We use a statement like temp is equal to temp.next to move the next node. What we can do is we can avoid this whole traversal with the help of pointer variable just like head node. We can call this variable tail or even rear. Let's call this variable rear for now, and also the variable which storing an address of head as front. In any insertion or removal, we'll have to update both front and rear now. But from now on, whenever we will perform enqueue operation, we can directly check where a rear node is and update its address to formulate a new insertion link. This simple addition of one pointer resolves our problem with the cost of insertion. Let's understand this scenario with the help of an example. Previously, we were traversing from head node to the tail node, but now, as we know the location of tail node, there is no need for any traversal. We can directly update the address part of rear node to make a link for new node. Here, the new node with data element 7 will be linked to the previous node, and the rear pointer will also be updated to point towards the newly inserted node. Now, the complexity for both the operation will be big of 1, which means we can now begin with the coding implementation of queue using a linked list. So, let's dive directly into that. In order to get started with our coding implementation, we'll need to load some dependencies that are called as header files. I have already included those header files here. So, first of all, we'll declare a structure to create nodes for our linked list. And inside this structure, we'll initialize data and address part. So, let's get started with creation of this structure. Struct node. Now, the initialization of data and address part. Int data struct node star next. Now using this created structure, we will initialize front and rear pointers. So let's create this front and rear pointer. Struct node star front is equal to null. Similarly, struct node star rear is equal to null. The declaration of variables that we have done here is in global scope. The reason behind that is to make sure that these variables will be accessible to all the functions. So moving forward, let's work out the primary queue operation. We'll start with enqueue operation. So let's create a function for that. Void enqueue, and inside this function we'll pass an argument int x to insert a element. Now inside the enqueue function, we'll take an integer as an argument. In this function, we'll create a new node for purpose of insertion. So let's create that new node. Struct node star temp is equal to struct node star malloc size of struct node.
So with this size of function, we have allotted the size of address part as well as the data part. One more thing I want to tell you guys is I am using malloc in C here for dynamic memory allocation. If you want to implement this code using C++, then you can use new operator instead of malloc. The purpose of using malloc here is to create a node in dynamic memory. Now, moving ahead, we can start working on two cases of enqueue operation. Primarily, there won't be any element inside the queue. So for the first insertion, we'll manually set both front and rear to the address of this newly created node. So to do that, first we'll have to create a if condition. If front is equal to null and rear is equal to null, front is equal to rear is equal to temp, which is nothing but the new created pointer variable, and will return the control. If this condition fails, that means there are already some elements present inside our queue. So using else condition, we can write another statements rear dot next is equal to temp and rear is equal to temp. Basically, these two lines of code are just updating the address part of the next node along with setting the temporary data into rear node's data field. This code will be further clear if I'll show things moving in simulation. So let's revisit PowerPoint for that purpose. Let's say initially we have an empty queue, so both front and rear will be null. Null is only a macro for address 0. At this stage, let's say we are making a call to enqueue function passing number 2 as an argument. Now let's go through the enqueue function and see what will happen. First, we'll create a node. The data part of this node will be set as 2 and the address part will initially set as null. Let's say we got this node at address 100. So a variable named temp will store this address. Right now, the front and rear both are null. So we'll go inside this if condition and simply set both front and rear as 100. After the first enqueue operation, our queue will look like this. Let's say we are making another call to enqueue function at this stage, passing number 4 as an argument. Once again, a new node will be created. Let's say I got this new node at address 200. This time the queue is not empty. So in this function, we'll first go to the statement rear.next is equal to temp. So we'll set the next part of this node at address 100 as the address of a newly created node, which is 200. So we'll build this link now. And now we'll store the address of this new rear node in this variable named rear. So this is how my queue will look like after the second enqueue operation. I hope that you guys are clear with the implementation of enqueue operation and the working of its code. Let's deal with the next queue operation named as dequeue in our code editor. Now inside this dequeue function, I'll create a temporary pointer to the node in which I'll store the address of the current front or head node so that we can directly delete it. So the statement I'll write for that is struct node star temp is equal to front. Now the first condition that we'll write in this dequeue function is underflow error. So let's begin with if block. If front is equal to null, printf queue is in empty state /n and return the control to the next function. Otherwise, in next case, when both front and rear will be equal, we'll set both these pointers to the null manually. So to do that, we'll insert another if block. If front is equal to rear front is equal to rear is equal to null. This if block will get activated when there is only one element inside the queue. In all other cases, we can simply make a front point to the next node. So we'll simply do a front is equal to front dot next. So for that, we'll write else block, else front is equal to front dot next. In all three previous mentioned cases, we are trying to remove elements, and that can only be done by implicit call of function free. So let's call function free to delete the front node from our queue. So the statement that we'll write is front free the temporary variable, which is actually storing the head node address. Next, we'll work on peek operation, and for that we'll create a new function int peek. Basically, the peek function is used to extract a value of front pointer. For front pointer, we will simply check if the queue is empty. If it is empty, then obviously there is no element at front node to extract. But if it is not empty, then we can extract a value from front pointer. So for that, we'll create a if block if front is equal to null, which also means the queue is empty. Then we'll return printf queue is empty /n. Otherwise, we will return the data present at front node. Now we have implemented all important queue functionalities, but we won't be able to check the state of queue with the help of these functions. So let's formulate one more function called as print to visualize our queue. So let's define this function void print Inside this function, we'll create a temporary pointer struct node star temp is equal to front. We are initializing this temporary pointer to the front so that we can traverse the whole queue elements using iterator element. So moving forward, let's create this iterator element using a while block. So the statement that we'll write for that is while temp is not equal to null, printf modulus d comma temp dot data. And we will set temp is equal to temp dot next. This is nothing but the traversal of linked list. Now we'll also printf /n so that all elements will be printed in order. With this, we have completed the implementation of print function as well. Now let's work on our driver method called as main function to contemplate the output of our program. Inside this, we'll make call to the enqueue function, enqueue to, and we will print the state of our queue using print function. Next, we'll make call enqueue for, and we will also print the state using print function. Next, we'll make call to enqueue6 and we'll also print the state of our queue at this instance. Now, after this, we'll dequeue few elements, dequeue, and we'll print the state. Next, we'll enqueue one more element, enqueue8. Now that we are done with the coding implementation of queue using linked list, let's execute the program and visualize the output. This is the output that we have received. Let's compare it with the calls that we have made in order to judge its correctness. The first call that we made was enqueue2. So the print function has printed 2 over here. After that, we inserted element 4 and 6 and our print function has printed the state after these operations as well. Next, we deleted the element present at front pointer, which is 2. So after deleting 2, the output that we got is 4 and 6. Finally, we inserted one more element to check if it is getting inserted at the rear end. And that element was 8, which is exactly inserted at the rear end of queue.
Introduction to priority queue. Primarily, we will have a look at the real-life example of priority queue to understand it better. A hospital emergency queue is almost an ideal example of priority queue. When you go to the hospital, you must have observed that the person who needs immediate medical attention will be treated first, irrespective of his arrival at the reception. That means treating a person who is in agonizing pain or in emergency medical condition is the priority of the queue of patients. Priority queue in computer science also works with same approach. So what exactly is this priority queue? Well, a priority queue is an abstract data type that operates similar to the normal queue except for the fact every element has certain priority assigned to it. This definition of priority queue suggests that this particular type of queue also follows the same restrictions for insertion and deletion of data elements. The insertion in the priority queue will only be achieved at one end and deletion at another or opposite end. Additionally, the priority of data elements will determine the order of removal. The elements which has higher priority will leave the queue at first, and the elements which has lower priority will definitely leave the queue at last. As a side note, I would like to tell you guys that the priority queue only supports the elements that are comparable, meaning the data that we are going to insert into priority queue must be orderable. The compiler should not be facing any difficulty while comparing these data elements. Otherwise, the execution of a priority queue will definitely fail. Moving ahead, let's have a look at an example of priority queue. In this priority queue, we will insert 7, 2, 45, 23 and 12 respectively. These elements are not ordered. So how the priority queue is going to store them in order? Well, at the time of insertion, the priority queue conducts a comparison of each element with every other element present inside a queue to store them in order. But as there is no element inside a queue, so the first insertion, that is an element with value 7, will be attained. Followed by that, the next element will be inserted in a queue. Since the newly inserted element is smaller than that of previously inserted element, we'll swap their positions in order to maintain order. Remember, the element with least value will have a higher order and the element with greatest value will have a least priority or order. Now we will insert the next element in a queue, that is 45. As 45 is a larger element than the elements inside the queue, there is no need to shuffle elements. When we make the next insertion, the element 32 will get inserted at index 3. Now this element is smaller than that of 45. So the algorithm will have to swap the locations of these elements. Now we will perform the final insertion into our queue. We will insert 12 at index 4 now. But as you can see, this element is smaller than both the previous elements. Thus the algorithm will have to swap their positions. Now 45 will reach the end of queue as it is the element with highest value, and 2 will remain at the front of queue as it is the least valued element. As a humans, we could see the numbers visually inside the priority queue, and further, we can easily arrange them. But how does the machine know this? Does it restore all the elements inside the priority queue before each insertion? No. Obviously, that would be highly ineffective as there will be n comparisons for insertion of n elements, leading to time complexity big O of n square. This is an enormous time complexity which we cannot allow in any software application. We will understand how the priority queue manages to reduce this time complexity in upcoming topics. But right now we will contemplate different properties of a priority queue that we have learned from previous example. The first property of priority queue suggests that each element has a certain priority assigned to it. That priority might depend on value of data element. It can be either larger or smaller. The next property states that element with higher priority will leave the queue at first, where the element with least priority will leave the priority queue at last. Further, if two elements have the same priority, then the element will be removed from the priority queue based on their arrival. That means the element which arrived at first out of the elements having same priority will be removed first. Now, moving ahead, we'll deal with the representation of priority queue using a linked list, as usage of arrays is not an ideal way to implement priority queue. If we consider array implementation of priority queue, then inserting items into the sorted array will cost us big O of n. And in general, processing each element will further cost us big O of n square as discussed previously. So in this tutorial, we'll just look into the linked list representation of priority queue. We will understand the representation of priority queue with the help of an example. Initially, let's say there are 3 elements inside a linked priority queue and all of them are in order. 3 being the least element has highest priority, where 43 has the least priority. The purpose of keeping 3 at the head node is that we want our priority queue to delete elements according to their priority. Now, we want to insert a new node consisting of data element 2. And as the data element is smaller than the element at head node, that is 3, so this new node should be inserted prior to it. This particular scenario of insertion seems pretty perfect as it does not cost us more time. But what if the element is significantly larger than all the nodes in queue? For instance, let's say we want to insert 45 as a new element. In that case, primarily it will be compared with element 2, and as 45 is larger than 2, our temporary pointer will move to the next node for comparison. Now, 45 will be compared with element 3, and again the temporary pointer will be moved to the next node for comparison. After 2 comparisons, the temporary pointer has reached element 17 for performing the next comparison. And here also 45 is larger than 17. So the temporary pointer will again move towards the next node. Now finally, our temporary pointer has arrived at the tail node consisting of element 43. Again, in this case, the element 45 is larger than 43, thus the new node will be inserted after node containing data element 43. From this specific example of insertion into a priority queue, we can clearly see that there are n comparisons leading to the time complexity big O of n, where the complexity of deletion remains constant, that is big O of 1. While understanding the representation of priority queue, we came across some facts that make priority queue implementation using linked list quite vulnerable. So here we will again try to recall them. The first drawback of priority queue implementation using linked list is that it costs us big O of n for inserting a new element. Further, it also costs us big O of n for peak operation. And as memory and time management is the purpose of data structure, hence we must try to analyze other implementation strategies. That is why in upcoming slides we'll look into different approaches to implement a priority queue. There are 3 approaches that implement a priority queue with complexity less than big O of n square. We have already discussed the linked list, so let's also look into other 2 approaches. Binary heap and binary tree provides almost similar complexity. These approaches cost us big O of log n for insertion and deletion, and big O of 1 for peak operation. But which one of these operations is most optimal approach to implement priority queue? Well, to answer this question, we again need to discuss about memory management in the case of both these data structure. You guys know that binary heap data structure is implemented using arrays. And since it utilizes arrays, there is always a better locality of reference as well as operations become more cache friendly. The binary search tree uses pointer to implement front and rear node, which definitely takes up more space in memory. Due to that, building a self-balancing BST costs us big O of n log n, where binary heap just costs us big O of n. These facts clarify that the binary heap is the best data structure to implement a priority queue. Now you must be thinking about what exactly the heap is and how does it work. So moving forward, we'll look into the definition of heap and its properties. Basically, a heap is a tree-based data structure that satisfies the heap invariant, or in simpler words, heap property. The heap invariant states that if A is a parent node of B, then A is ordered with respect to B for all nodes A and B in heap. What that means is the value of parent node is always greater than or equal to the value of child node in the heap, or other way around, the value of parent node is less than or equal to the value of child node for all nodes in a heap. Further, there are two types of heap named as max heap and minimum heap. First, we will look into max heap. The max heap is heap in which value of parent node is greater than the value of child node. For this particular example of max heap, you can see that the root node is the biggest element in tree and each child node is smaller than its parent node. The next type of heap is minimum heap. The min heap is heap in which the value of parent node is less than the value of child node. In this specific example, you can observe that each child node is larger than its parent node and the element at the root node is smallest element of the heap. Both the structures that we have discussed are binary heaps as every node has only two children. In upcoming slides, we will discuss some complex structures of heap data structure to better understand how we can judge if a tree-like structure is heap or not.
Okay, so you can see a tree-like structure on your screen, and we are supposed to check whether if it is a valid heap data structure or not. But actually, here I would like you all to give it a try by yourselves. You can also pause this video if you want, but here I will provide you with a short moment to inspect this structure. Alright, I can clearly say that this is not a valid heap data structure. As you can observe, the highlighted part is violating the heap invariant. Moving forward, let's analyze another tree-like data structure to consider if it is a valid heap or not. Well, yes, this is a valid heap because even though this one is strangely structured, we are free to move around the visual representation of nodes to make it organized. Now you all must be thinking how we can do that. Well, we'll understand that scenario in upcoming slides. Now, how about this one? Is this a valid heap? No, right? This is not a valid heap. This structure is not even a tree as it forms a closed cycle and every heap must be a tree. So it's pretty clear that this is not a valid heap. Now, what about this one? Is this a valid heap? Yes, this is a valid heap as it satisfies the heap invariant that all the child nodes must be greater than or equal to or smaller than or equal to its parent node. Now, this is the last structure that we are going to check if it is a valid heap or not. What you guys think? Is this a valid heap? Well, I think it's pretty clear that this is not a valid heap, but it can be converted into a heap by making a one small change. Now, if we make 6 as our root node, then this structure will get converted into a max heap, which is absolutely a valid heap. I hope you all are clear with the heap invariant and how to judge if a given tree is a valid heap or not. Now moving ahead, we'll discuss the different types of priority queue. Basically, there are two types of priority queue based on the priority of elements. If the element with smallest value has highest priority, then that priority queue is called as min priority queue. And if element with higher value has the highest priority, then that priority queue is known as max priority queue. Furthermore, it's vividly clear that the min priority queue can be implemented with a minimum heap, where the max priority queue can be implemented using maximum heap. Moving ahead, we'll deal with the operations in priority queue considering the heap as implementation strategy. The common operations that we can perform on priority queue are insertion, deletion, and peek. But there is one more hidden additional operation that gets performed during these operations. That operation is called as heapify. Heapify manages the priority of data elements in a heap by shuffling the data elements after new insertion or deletion. First of all, we will understand how insertion in priority queue happens with the help of an example. In this example, we are inserting a new data element that is 43. But due to this insertion, the structure disobeys the priority queue invariant that the parent node of the max priority queue must be greater than its child node. Now, the heapify operation solves this problem by rearranging data elements by carrying out the comparison. In this particular case, 43 becomes the parent node where 40 becomes the child node. The next up is deletion. As we know, the highest priority element will be the first to leave the priority queue, and further, it is stored at the root node of a max heap. So definitely, the element present at the root node will get removed. But due to this operation, the order of priority queue gets affected. However, the heapify operation comes to the rescue. It reshuffles the elements of the priority queue to rearrange them in order. The next operation that we are going to discover is peek. The peek operation simply returns the element present at root node without removing it, and it is easily accessible. Thus, the time complexity of this operation is big of 1. I hope you all are clear with the operations that can be performed on priority queue. Moving forward, we'll try to implement them with the help of minimum heap. As discussed earlier, while implementing a heap data structure, we know that all the elements will get stored in an array, and we don't have any pointers pointing to either child or parent nodes. So how exactly does the heap data structure remember nodes like parent nodes and its left or right nodes? Well, if you have learned binary trees, then you must know the formulas present on your screen. These formulas determines the left child, right child, or even the parent node of any binary tree. Let's understand how this phenomenon works with the help of an example. We'll begin with index 0. If we enter 0 in this arithmetic expression, then we will get 1 and 2 as output. That means the element at index 1 will be the left child and element at index 2 will be the right child. And tree structure will look like this. Now, moving ahead, let's take an example of index 1. For index 1, the left child will be at index 3 and the right child will be at index 4. Similarly, for index 2, the left child will be at index 5, where the right child will be at index 6. Using these formulas, we'll be implementing heapify and primary queue operations. So note them down for further reference. Now moving further, we will visit code editor to implement priority queue data structure using C programming language. Previously, I mentioned that heap is implemented using arrays. So to begin with heap implementation, primarily we will create a structure consisting of different variables or objects needed to implement heap data structure. So let's create a structure, struct heap consist int size, int count variable, and int star heap array, which is a dynamic array that we are creating here. And next, we'll also declare a pointer to heap structure along with size and count variable in a global scope. So let's do that. Int star heap comma size comma count. We'll create one more variable, int initial underscore size, to represent the initial size of our priority queue, and let's assign it value 4 for now. Okay. Now it's time to allocate memory to our heap array. For this purpose, we'll create a new function called heap underscore init. So let's create this function, void heap underscore init, and inside it we'll pass an argument struct heap star h, which is a reference of this structure that we created previously. Okay. In this function, let's initialize the variables that we have created inside this heap structure. So for that, we'll initialize h arrow operator count is equal to 0. Similarly, h arrow operator size is equal to initial underscore size, and h array is equal to int star malloc size of int star 4. This statement is just allocating 4 integer variables to our heap array. Basically, our heap array is dynamic data structure. That's why we have to provide it with dynamic memory using malloc. If you are using C++ programming language to implement this data structure, then you can use new instead of malloc. Moving forward, now we'll work on our condition if not h arrow operator allocates memory to heap array, then printf error while allocating the memory, and that /n. Next, we will write exit command. Okay. With this, we have successfully implemented our heap init function. Now moving ahead, let's implement heapify function to move the nodes. For that, we'll create a heapify function void max underscore heapify int star data int log int count. So all these are required variables to implement this heapify function. that we have passed in argument for this max simplify function. Now let's create few more variables that we need. Int left, comma right, comma largest, comma temp. Now, as discussed earlier, left will be equal to 2 star location in array plus 1, and right will be equal to left plus 1. Now let's say largest is equal to LOC, and we'll work on conditions now. If left is greater than or equal to count, and data left is greater than data largest, that is the location we have stored in largest variable, then largest is equal to left. With this block, what we are doing is we are checking if the element at location left is greater than the element at recent position, and the value at left is also greater than the value of recent location. If these conditions are true, then we will set the recent location as left. And here we are getting signal that there is semicolon missing over here, so we'll add it. Okay, now let's work on next condition. Now we will check the value at right position. If the recent location is greater than the right and the value at right is greater than the largest value, then element at largest will be set to right. So for that we'll write condition if right is greater count and data right is greater than data largest, then largest is equal to right. Otherwise, if largest is not equal to location, then we will store the data present at location in temporary variable, and data LOC is equal to data largest. This is a swapping operation that we are carrying out here. And next, data largest is equal to 10. And now we'll make recursive call to our heapify function max underscore heapify data comma largest comma count. With this, we have successfully completed our heapify function. Now we will work on insertion operation on priority queue. Let's call this function heap underscore push. because we are treating this structure as heap, right? So in heap, insertion is called as push operation. So we'll call it void heap underscore push, and we'll pass arguments struct heap star h int value, and inside this function we'll create few more variables int index and parent. If you guys remember, the initial size that we have allocated to our array is 16 bytes. You can verify with this statement here that we are providing 16 byte size to our heap array. But what if you want to insert elements more than 4? Then what we'll do? Well, for that, we'll need to increase the size of our heap array. So we'll do that here. For this resize, we'll create if condition if h dot count is equal to h dot size, then h dot size plus equal to 1, and h dot heap array is equal to realloc h dot heap array size of int star h dot size. Basically, we are using realloc function in C to extend the dynamic memory space for our heap array. And in order to increase the size, we have to increment the size variable first. So that's what we have done in this statement here. And now, once done with this, we'll check if our dynamic memory is getting allocated or not. So for that, we'll add one more if condition inside this if block. So it can be called as nested if you guys want. Dot heap array, then exit -1. Now we'll move out of this if block and we will set index variable to h dot count plus plus. Basically, we are iterating with help of index variable here. So next we'll add for condition for loop index to index is equal to parent. And inside this condition, we will make parent node is equal to index -1 by 2. This is nothing but the formula that we have discussed in previous part. Now we'll add one more condition inside this for loop if h dot heap array parent is greater than or equal to value, then we will break this for loop. Otherwise, h dot heap array index will be equal to h dot heap array parent. Now we'll move outside this for loop and we'll add one more condition of insertion, that is h dot heap array, and at position index we will add the value provided by user using argument to heap push function. Okay, with this we have successfully created our heap push function. Now we'll move towards the next function, that is heap underscore delete. For that we'll create new function heap underscore delete, and let's make this function integer, and we'll pass struct heap star h as an argument. We will create one more variable temp is equal to h arrow operator heap array, and inside this we'll pass a negating index. That means we are using this temporary variable to traverse through all list of elements. So for that we'll write dot dot minus minus h arrow operator count, which will decrease count one by one. Now next we'll add condition f h arrow operator count is greater than or equal to h arrow operator size plus 2 and h arrow operator size is also greater than the initial underscore size. Okay, then what we will do is we will set size to negate itself by 1 for each iteration, and then we will add h arrow operator heap array is equal to realloc h dot heap array comma size of int star h arrow operator and size and semicolon. So basically what we are doing here is we are checking if count is smaller than the size of heap plus 2 and the dynamic size of queue is also larger than initialized size, that is 4, then what we are doing is we are reducing the size for deleting an element using this statement, and in next statement we are reallocating that deleted space. So this is how this if block works. Now moving forward, we'll add a condition to check if memory is getting reallocated or not. For that, we'll write condition if not h arrow operator heap array. Then what we'll do is exit with -1. Okay, now let's move out of this if block, and now we will set this removed variable to h arrow operator heap array and index 0. So if you guys remember, 0 is the index of the highest element in our maximum heap. What I mean here is the element with highest value is stored at index 0 for max heap. Now moving forward, to delete this element, what we'll do is we will set h dot heap array and index 0 is equal to temporary variable or pointer that we have created previously, and next what we'll do is we'll call max underscore hippify function to rearrange the structure of our priority queue which has been shuffled due to this delete operation. Now for that we'll pass arguments our heap structure, that is heap array, and next the index which was removed and the count variable, and we'll return the removed element. Okay, with this we have successfully implemented our delete function. Now to understand the order of deletion in priority queue, we will implement one more function called as mtpq. So let's create this function. And in this function we'll pass the reference of heap structure in order to operate on it. So let's pass the structure heap star h, and inside this function we will create a while loop h dot count is not equal to 0, then printf modulus d and recursive call to heap delete function in which we'll pass h. Now we are done with this mtpq function. Further, we'll create one more function to visualize our priority queue. Let's call this function void heap underscore display, and inside this we'll pass structure heap star h, and now we will create one iterator element, and using that iterator element we'll create for loop I is equal to 0 to I is greater than arrow operator count plus plus I, and inside this for loop we will print the elements present in our queue using this format modulus d, and we'll call heap array. But for that we'll need to call structure as well. Heap array, and we'll pass this iterator variable into it. Okay, and then next we'll get outside this for loop and we'll printf this to the next line using /n. Okay, now we have implemented all the required function for our priority queue. Moving forward, we'll work on our driver function, that is main method, to contemplate the result of our program. So for that we'll first call struct heap h, then we'll call init function to create heap structure, so heap init, and we'll pass the address of h. Next we will call heap underscore push function to insert element, and h comma 1. Next I'll copy this part, we'll paste it to insert another element. Now we'll insert 5 here. Next paste, and we'll pass 3. Next we'll insert element 7. Next we'll insert element 9, and after this we'll insert element 8. Okay, so now let's display the elements inside our heap using heap underscore display function, and let's pass an h object to print it, and again we'll call empty pq function, empty pq, and we'll pass h, and after deleting all elements it will return the state of our heap array again, or our priority queue. So finally we'll add return 0 statement, and now our code is ready. So let's compile it and check it if it works fine or not. So we are getting 4 errors here guys, so we'll need to resolve them. First we'll need to check line number 82. So for 82, okay, here we haven't added semicolon, so I think this should be fine now. Still we have 2 errors. Before I reach there, so let's recompile it and check it if it is working fine now. So we have received our output now. Now if you look at our output is printing elements 9, 7, 8, 1, 5 and 3. And deletion of elements is also happening according to their order. So 9 is getting deleted first after 8, 7, 5, 3 and 1. So that means our elements are getting removed in proper order. Further, we can say that our program for priority queue implementation works fine. Now, if you guys are worried about this program, then not to worry. We have you covered. You can mention your email IDs in comment box below and we will send it over to you. Remember guys, we can make comments private to protect all your data. So you can fearlessly put all your email IDs in comment box below. Now we will discuss applications of priority queue to understand its importance. The first application that we are going to discuss is use of priority queue in Google Maps. You must have used Google Maps several times to navigate from one city to another or from your location to nearest desired location. Have you ever wondered how Google Maps managed to do that? How does it provide an optimal path to reach your location? Well, Dijkstra's shortest path algorithm implemented in Google Maps actually manages to do that by gaining access to all possible paths. This algorithm uses the priority queue to maintain all the paths in order. Let's understand how it works in detail. Now, when you provide the location of place you want to reach via your mobile device, Google Maps feeds the data of all possible paths to Dijkstra's algorithm. Those paths or road are stored in minimum priority queue considering the distance as parameter for priority assignment. And we have learned that the minimum priority queue maintains the lowest value at the front or root node. This is how the priority queue helps Google Map to search for an ideal path for reaching destination location. The next application that we are going to discuss is data compression in WinZip or gzip. These applications use Huffman encoding algorithm to reduce the size of files. Huffman coding is a lossless data compression algorithm, and in this algorithm, a variable length code is assigned to input different characters. The code length is related to how frequent characters are used. Most recurring characters have the smallest codes, and longer codes are for the least frequent characters. This is how the generated codes will maintain the complete data while utilizing less memory space. Let's understand how this process works with the help of an example. Let's say our text file contains these random characters. The Huffman encoding algorithm creates codes for each character based on its number of occurrences. For instance, the frequency of character A is more prominent than B, and character C has less frequency. So the length of code A is smaller than B, and length of code B will be smaller than C. Now, according to the amount of generated code, the priority queue will determine the priority of characters and will store them. These codes takes less size than the actual characters in memory space, and due to the mapping of occurrences, data does not get lost. I hope now you guys understand why the priority queue is treated as an abstract data structure itself and why it is the better version of queue data structure. What is DQ? DQ is an abbreviation for double-ended queue, and as the term double-ended queue suggests, it is a type of queue with some advanced features at both of its ends. But previously, we have learned that the basic queue data structure must perform insertion from one of its end and deletion from another or opposite end. So what new limitation or feature does this particular type of queue brings? Well, the DQ extends the concept of a linear queue by implementing insertion and deletion at both of its nodes. By that, what I mean is the DQ data structure is acquainted with the possibility to insert and delete new elements at any node. That is why DQ is concerned as more generalized version of queue data structure. Now, moving ahead, we shall understand the key properties of DQ. The first property of DQ states that the DQ can use the LIFO principle for inserting or removing elements. The last in first out principle is used while implementing stack data structure. And according to this principle, the queue elements must be inserted from one end and should also be removed from the same end. For instance, we are storing some elements inside this queue structure which is performing both insertion and deletion from one end. However, When deletion begins, the element inserted at last will be removed first, whereas the element stored at first will get removed at the end. This property clears that the DQ can inherit all the properties of stack data structure. The next property of DQ states that the DQ can use the FIFO principle for performing both insertion and deletion operations. That means the element which enters inside the queue at beginning will also leave the queue at first. Further, the element which entered at last can leave the queue at last. Both of these properties displays the uniqueness of this particular type of queue data structure. Now in upcoming slides, we will understand different types of the DQ. The first type of DQ we have is termed as input restricted queue. This terminology itself suggests that this particular type of DQ will have some restrictions while performing enqueue or insertion operation. In this type of DQ, the insertion can only be performed from one end, where deletion can be performed at both of its ends. The representation of DQ shown below explains how the operations in this type of DQ will get accomplished. The next type of DQ is output restricted DQ. This term makes clear that this type of queue will have some restrictions while performing deletion operations. In this specific type of queue, the removal of elements can only be performed from one end, where the insertion can be performed at both of its ends. This particular structure of a queue explains how the different operations will take place in this type of DQ. Now here is the interesting question that we want you all to answer. Based on the properties of DQ that we have discussed till now, which of the following data structure will be more ideal for implementing DQ in data structure? What I mean by ideal is the time and space complexity for implementation strategy that you decide should be minimum. The options that we have are circular array, singly linked list, and doubly linked list. It will be interesting to see how many of you guys will get this right. So guys, do leave your answers to this question in comment section below. In a week's time, we'll be announcing the right answer and you all can check it out. On that note, let's dive further and understand the representation of DQ using circular queue. And yes, circular queue is one of the answers for previous questions. We'll understand why it is best in upcoming slides. But please check the complexity analysis of other two strategies to decide your answer for the previous question, as multiple answers can be accurate for that question. Now let's understand what a circular queue is. Well, a circular queue is nothing but the extended notion of linear queue, as it follows the first in first out principle, with the exception that the last position of this particular queue is connected to its first position, making a circular link. This circular link is responsible for naming of this queue as circular queue or ring buffer. Let's understand how a circular queue operates with the help of simulation. This is the illustration of a circular queue having size 5. As the position of rear pointer keeps increasing, a new element will be inserted in this queue until the rear pointer reaches the end of queue. But what if we perform DQ operation now? If we perform the deletion, then the empty space will get created at front of queue. However, this space can further be utilized in this particular type of queue by making circular incrementation of rear pointer or circular link. So, if we increment the rear pointer from its index 5 to index 0, we can utilize empty space by making new insertions. Using this feature of circular queue, we can implement both insertion and deletion at both the ends of queue. Let's understand how we can do that in upcoming slides. The first type of insertion is a pretty ordinary one. In this insertion, we'll increment the position of rear pointer to insert a new element. The arrow shown in blue is rear pointer and the arrow shown in orange is the front pointer. So as you can see, once we increment the rear pointer, new elements get inserted. This is how the insertion using rear node happens. Now, what if we want to perform insertion using front end? In order to perform the insertion using front node, we'll have to make front pointer reach to the end of queue. The only possible way to achieve that is to set front pointer equal to max size -1 manually. This command will allow a front pointer to reach the end of queue for performing insertion. And for further insertions, we'll just have to decrement the front pointer location for inserting new elements. This is all about insertion. Now that we have implemented insertion from both ends, let's move on to the deletion operation. Primarily, we'll look into the deletion using front node. In order to delete elements using front node, we'll have to increment the front pointer until it reaches the end of queue. And once it reaches the max size, we'll use circular incrementation to bring the front pointer to the beginning of queue. While performing these incrementation, meanwhile the elements will be removed from the queue. Next up is deletion using rear end. For performing deletion using a rear pointer, we'll have to decrement its location. Once we decrement the rear pointer location, the element will get removed from the queue. Now moving ahead, we'll look into the different operations that can be performed on a double-ended queue. Basically, there are 4 primary operations in the DQ which we have already understood in the representation of DQ using circular queue. These operations are insertion and deletion at the front and insertion and deletion at the rear. Additionally, the circular queue implementation of DQ cost us big of 1, which is the most optimal complexity that we can hope for. Having said that, let's dive into the implementation of these operations using a circular queue. We'll implement a double-ended queue using circular queue. In order to do that, we'll use C programming language and one-dimensional arrays. So without wasting any time further, let's move to the code editor. Now, in order to get started with implementation of DQ, we'll have to create array and pointer variables. So let's do that. Int, we'll name this array as DQ and we'll provide 100 as initial size. Next, we'll create pointers and rear is equal to -1. Now, we'll also define the maximum size for our queue using define call. Size as 5. After done with this initialization process, we'll start working on insertion from front node. We'll declare a function named as void front insert. So let's do that. Void front underscore insert. And inside this function will pass an argument int z to insert an element. Now, while performing insertion, we should always check if the queue is full or not. Because if it is full, then the insertion won't be possible. So for that, we'll write condition if front is equal to 0 and rear is equal to size -1 inside and braces or front is equal to rear plus 1 printf DQ is full insertion it's not possible. Okay. Otherwise, if both the front and rear node are pointing to null memory index or -1, we'll manually set our front pointer to index 0 to make the first insertion into the queue. And we will insert the element at new location or index 0 where the front pointer is pointing. So for that, what we'll do is we'll write another condition with else if block else if front is equal to -1 and rear is equal to -1, then make front is equal to rear is equal to 0 and dq front is equal to z. Now, if we want to insert the element at the last node of Q, then we need to set front pointer to the max size -1 location. To do that, we'll write this condition, else if front is equal to 0, then front is equal to size -1 and dq front is equal to z. If all these above mentioned conditions fail, then the front pointer is already at the last part of Q and it just need to decrement its location for inserting element in empty spaces as discussed previously. So to do that, we'll write one more condition using else block. So let's do that. Else front is equal to front -1 and dq front is equal to z. Now we have successfully implemented our front insert function. So let's move forward and work on another function that is called as void rear underscore insert, and we'll pass z as an argument to insert an element. Now, as done previously, we will first check if our queue is full or not. So let's do that using if condition. If front is equal to 0 and rear is equal to size -1 inside braces, or front is equal to rear +1, then printf dq is full. Next, if there is no element in an array, we'll manually set the rear pointer to index 0 for new insertion. So for that, we'll write condition else if front is equal to -1 and rear is equal to -1, then set rear is equal to 0 and insert dq rear is equal to z. Otherwise, if rear pointer is already at the end of Q, then we will bring it to the beginning of Q. So for that, we'll write condition else if rear is equal to size minus 1, then bring rear to index 0 and dq rear is equal to z. If all these mentioned conditions fail, then what we'll do is we'll write else condition and we'll simply increment our rear pointer to make an insertion. So for that, what we'll do is we'll create else block and we inside it we will do rear plus plus and we will set dq rear is equal to z. With this, we have successfully implemented void rear insert function. So now let's move into deletion functions. First, we'll create void front dq function, void front underscore dq. And there is no need for any argument for this function. To begin with this function, first we'll have to check if dq is empty because we cannot delete elements if there is no element to delete. So for that we'll write if condition if front is equal to minus 1 and rear is equal to minus 1, then printf there is no element to delete inside this dq. In the next condition, we'll check if there is only one element inside the dq. If there is only one element, then we'll set both front and rear to minus 1 manually. For that, what we'll do is we'll create else if condition. Else if front is equal to rear, then printf we'll add slash n to take this to the next line. The deleted element from the front is modulus d comma dq front. And we will set front is equal to minus 1. Similarly, rear is equal to minus 1. Now, if both these above mentioned conditions fail, then we will delete the element from our front node. The first removal will be in a case when the front pointer is at the end of queue. So for that, we'll write condition else if front is at end of queue, that is size minus 1. Then what we'll do is we will printf slash n the deleted element from the front is modulus d comma dq front comma. And another condition will be when the front pointer is at the beginning section of a queue. For that, we'll write else condition printf /n the deleted element from the front edge modulus d, comma dq front. With this, we have successfully implemented our front dq function. Now let's move towards next function, that is deletion from the rear end. For that, we'll create new function named void dq underscore rear. And this function also does not need any argument. So next, what we'll do is we'll create condition to check if the queue is empty or not. So if front is equal to -1 and rear is equal to -1, then printf /n there is no element to delete inside the queue. Now let's move to the next condition. In next condition, we'll write else if front is equal to rear, then printf some statement and set front is equal to -1 along with rear is equal to -1, and that statement will be the deleted element from the dq using rear node edge modulus d, comma dq rear. Now, if both these above mentioned conditions fail, then we'll have to delete the element from our rear node. The first removal will be in a case when rear is at the beginning portion of a queue. For that, let's write a condition else if rear is equal to 0, that is at the beginning part of queue, then printf some statement and rear is equal to size -1, that is setting it to the max size of queue, and the statement that we will return is \n the deleted element from the rear node edge modulus d, comma dq rear. In other cases, we'll just have to decrement the size of rear pointer and delete the element. So for that, we'll write else condition printf some statement and set rear is equal to rear -1, that is decrementing the size of rear pointer, and the statement that we'll write is \n the deleted element from the rear node is modulus d and comma dq rear. Well, here is one spelling mistake, so let's remove it. Okay, so with this we have successfully implemented our void dq rear function. Now we will implement one more function to display the state of our dq. The name of that function will be void display, and this function also does not need any argument. So we'll begin with implementation of this function. For this we'll create an iterator element and we'll set it to the front pointer, and we'll printf \n elements inside the double ended queue are next line. We'll enter into while loop to print those element. I not equal to rear printf modulus d comma dq I, and will increase the value of I by I plus 1 modulus size, and outside this while loop we will printf modulus d dq rear. Okay, with this we have implemented all the required functionalities for our dq. So let's work on driver method, that is main function, in order to check the output of our program. So let's work on this main function. First we will insert few elements into our queue. So I will insert first element using front insert. Next let's insert one more element from front node using function front insert, and this element will be 23. Next we'll insert elements using rear node underscore insert, and we'll pass 17 now. Next we'll insert #12 and we'll insert one more element using this rear node only, insert 47. Now we will display the state of our queue after performing all these operations. And next we will dequeue few elements. So for that we'll use front dequeue function, and next we will dequeue from rear node. So dequeue rear, and after performing deletion operations we'll also display the state of our queue. So let's call display once again, and let's add one more command, return 0. Okay, so with this, we have successfully implemented our program for DQ implementation. So let's run it and check if it is working fine or not. Okay, so we are getting output here, but our display function is printing output in weird manner. So let's work it out. So all we have to do is we'll have to add space before modulus t here and here as well. So once done with this, let's recompile our code. Okay, so now our output is clear. So let's check if it is perfect or not. So the first insertion that we made was -5. Second was 23 from the front end. So 5 should be getting inserted before 23. So -5 is getting inserted before 23. But as we are inserting it using front pointer, so 23 is remaining at the front now. After these two insertions, we are performing insertions using rear pointer. The first rear insertion was 17, then 12, then 47, and these elements are getting inserted. So let me show you how they are getting inserted in exact same order. So look here. So elements inside the double-ended queue are 23, -5, 17, 12 and 47. That means the insertion is in right order. After that, we deleted the element from front node. So the front node is at 23, so 23 is getting deleted. After that, we deleted the element using rear node. So 47 is getting deleted from the rear node. We are still getting 23 here. That means the DQ function is incomplete, so we'll have to change it. So let's go to the DQ function, and I guess it was from front end. So we'll need to change code for our front DQ. So okay, so in this case we haven't brought our front pointer to index 0, so let's do that here. And once we do this, let's recompile our code again. Okay, so now you can see that the 23 is getting deleted. With this, we have successfully implemented our DQ function. Now let's move back to the PowerPoint and understand few applications of DQ. The first application that we are going to discuss in detail is palindrome checker. You all must have heard about the term palindrome. The palindrome is a specific word or number which reads the same backward as forward. For example, the word radar. It reads the same from both the ends. So using the DQ, we can implement the palindrome checker program with complexity big of 1. The string which you need to check will be inserted into a DQ, and after that it will read from both sides. If the reading is the same, then that string will be considered as palindrome. The next application of DQ is its use in multiprocessor scheduling. But what precisely is multiprocessor scheduling and why do we need it? Well, the system implemented in the old days used single processor scheduling to manage the computing processes. When multiple processes need to be executed by a single core or CPU, then the process takes more time to implement, and thus the system lacks computing power. But the multiprocessor scheduling implemented in modern computers resolves that problem using a double-ended queue. Suppose we have three processors in our system, and each processor has some processes to execute. Each processor maintains a D queue that contains threads that are ready to execute. The processor executes a process, and if a process creates a child process, then that process will be inserted at the front of the D queue of parent process. Suppose the processor P2 has completed the execution of all its threads. Then it steals the thread from the rear end of processor P1 and adds it to the front end of the processor P2. The processor P2 will take the thread from front end. Therefore, the deletion takes from both the ends. This is also known as a-steal algorithm in process scheduling.
In this session, we will learn about stacks and queues in data structures. What is a stack? So, to define stack in a more generalized way, we can consider stack as a linear data structure that follows LIFO order or last in, first out order. Or another way of putting it down is first come, last out order. So, some of the basic operations that can be performed on stack are insertion and deletion, and that can be done only at the end, which is called as the top of the stack. Now, let us understand the basic operations on stack. So, the three fundamental operations that can be applied onto a data structure like stack are push, pop, and peek. So, the push operation involves inserting a new element from the top of the stack. The pop operation involves removing the element from the top of the stack. And finally, the peek operation, which returns the topmost element from the stack without removing the element from the stack. Now we shall go through some generalized examples of stack. So some of the generalized examples of stack are, you can see a stack of books here and a stack of utensils, stack of coins and stack of dollars or bills. Now, let us go through a practical example based on stack in data structures. We shall be using C programming language for this particular example. So you can see that on my screen I have an example for stack data structure. Don't worry about the code. This code will be attached in the description box below and you can always have access to it, and you can run the same code in your personal system so that you have a deeper and better understanding of the program. Now let's quickly run this program. So there you go. You can see the program is getting executed now. So you can see that the program got successfully executed and the elements are being inserted into the stack. Now the elements are A, B, and finally the elements are popped back again, that is B, A, and the last element that is popped away from the stack is A, and you can see that the stack is currently empty, so top is pointing to -1. Now with that, let's get back to the presentation again. Now let us understand some of the applications of stack. So one of the applications of stack is function call or recursion. The recursive function call is also known as the called stack. Whenever a function is called, then the function goes to the top of the stack. Now another important application of stack is expression conversion. There are three types of notations, that is prefix notation, infix notation, and postfix notation. So these particular notations can be taken care by using stacks in real time. Now the next one is checking parentheses. Stack is used to check if the given parentheses are balanced or not. Sometimes if you forget to add a parenthesis, then the compiler will throw an error. So using stack, this can be found if there are balanced parentheses used in your program or not. Balanced parentheses means opening and closing brackets are of the same type. That means if you have two open flower brackets, then you need to have two closed flower brackets. It should not be unequal. It should be completely equal to complete the code segment. Now another application of stack is expression evaluation. Stack can be used to evaluate the expressions. As you can see here, we have an expression that is 6 plus 2 star 3 minus 12 divided by 4. Now this particular expression will be evaluated based on the precedency table. So the stack is used to check the precedence and then the expression gets evaluated into the result, which is 21 right over here. Now another application is the Tower of Hanoi. Tower of Hanoi is a mathematical puzzle which consists of 3 rods and n number of discs of different diameters. All the discs are placed on one rod, one over the other, and in ascending order of size, similarly into a cone-shaped tower. Now we will enter into the next segment where we will discuss about queues. So what exactly is a queue? A queue is a linear data structure that follows the FIFO order, that is the first in, first out. whereas stack followed first in, last out. So this is one of the fundamental difference between stacks and queues. So we'll be discussing those in the next section. For now, let's continue with the operations on queue. The queue is an ordered list in which insertion is done at one end, that is called rear, and deletion is done at another end, which is called front. The operations on queue are enqueue operation that adds a new item to the queue. If the queue is complete, then there is an overflow condition. Dequeue operation is the operation which deletes an item from the queue, and if the queue is empty, then there is an underflow condition thrown as an exception. Now let us understand some of the basic examples of queue. You can consider the patients at hospital registration, and you can also consider an example of customers making use of ATM. Now let us understand the types of queue. So there are basically three types of queues. Those are circular queues, doubly ended queues, and priority queues. Now let us understand the circular queue. In a circular queue, the last element points to the first element to form a circular link. Circular queue is also known as ring buffer. Insertion is done at the rear and deletion is done at the front, as discussed before. Now we will go through the doubly ended queue. In doubly ended queue, both insertion and deletion can be done at both rear and front of the queue. Now the last one, the priority queue. In the priority queue, the nodes have same predefined priority. Insertion can be done as the arrival of the nodes. Node having the least priority will be the first node removed from the queue. Now we will go through a general practical example of queues, and then we will go through the applications of queues. Now on my screen you can see an example for queues. Don't worry about the code. This code will be attached in the description box below, and you can always have access to it and learn executing this on your own system. So without further ado, let's start to execute this code. So you can see that the code got successfully executed and the terminal is asking for us to give an operation. So the first one is to insert an element into the queue. Second one is to delete an element, and the third one is to display the elements in the queue, and the fourth one is to quit. Let's insert. So now let us insert an element into the queue, that is 10. Now let's try to display the elements in the queue. For that I need to select the option number 3, and there you go, the queue has element number 10. Now let's try to delete that element. For that we might have to choose the second option. So you can see that the element got deleted from the queue, and the element deleted from the queue is 10. And you have another choice now. So let's try to quit it now. For that I need to select the option 4, because we have seen how to insert, view, and delete the element. Let's not make further delay, and let's quickly enter into the next part of our session, that is the application of queues. So the first application of queue is breadth first search. Breadth first search, or BFS, traverses a graph in a breadthward direction and uses a queue to remember the next node to start a search. The second application is level order traversal in tree. Level order traversal processes all the nodes of a tree by depth. First the root, then the children of the source. Next one is first come, first serve CPU scheduling. First come, first serve FCFS is an operating system algorithm that works on queued requests and implements them according to their arrival. Now, the Fibonacci heap. Fibonacci heap is a data structure that implements priority queue operations consisting of the collection of heap order trees. Now, our last segment, that is the comparison between stack and queue. So at first, both stack and queue are linear data structures, and stack follows last in, first out, whereas queue follows first in and first out. And when you're considering stack, the insertion takes place at the top and deletion takes place from the top as well. Whereas when it comes to stack, the insertion starts from rear, but deletion or elimination of the element from the queue starts from the front. In stacks, the insert operation is called as push, and deletion process is called as pop. In queues, the insertion is called as enqueue and deletion is called as dequeue. In stacks, we mainly maintain one pointer to access the list, that is called top, which always points to the last element present in the list. In queues, we maintain two different pointers. The first one is the front pointer, which always points to the front element or the first element inserted in the list. And the next one is the rear pointer, which always points to the rear or the last element inserted into the list. Stack is used in solving problems that work on recursion, whereas queue is used in solving problems having sequential processing. So these are the fundamental differences between stacks and queues. In this session, we will learn about linear search algorithm, its complete logic, and how to program and implement it in real time. Now, let us try to understand what exactly is searching. Searching in data structure refers to the process of finding the desired element in the set of items. The selected item is called the target element. Any data structure such as an array, linked list, tree, or graph can be used for searching a set of elements. In data structures, searching can be categorized into two types. First type is the sequential search, in which we check the elements in a data list or an array one by one. In data structures, searching can be categorized into two ways. The first type is a sequential search, in which we check the elements in a data list or an array one by one. An example for sequential search is linear search. Now, let us learn about the next type of searching approach. The next type of searching approach is the interval search approach. Interval search divides the search in half by repeatedly targeting the center of the dataset. The binary search algorithm can be an example for interval search. We will go over the binary search algorithm in detail in our upcoming video. After understanding the logic of search and the types of search, we will get into understanding what is linear search algorithm. The linear search method is a simple search technique. In this type of searching approach, we perform a sequential search across all objects one after the other. Every element is examined, and if there is a match found, then the specific element is returned. Otherwise, the search will continue until the data gathering is complete. Let us go through an example for better learning experience. On my screen, we have the following elements: 50, 10, 20, 30, 70, 40, 90, 60 as randomly distributed elements. Let us imagine that our target element is 70. We found that our target element was 70 using linear search strategy. So, how does it work? In the next segment, we will look into the working terms of linear search algorithm. The simplest method of searching the data collection is the linear search. Starting from the beginning of the dataset, each element is examined until no match is found. The linear search is completed after the item has located. In the first stage, we compare the first element, that is 50, to the searched element, that is 70. We will go on to the next element because 50 and 70 are not matched. We will compare the second element, which is 10, to the search element, that is 70, in the next step. And once more there is no match found. Then we have the element 30 as the next comparison, and 70 and 30 are not matched. We have the next element, that is 20, in the fourth phase, and there is no match when we compare 20 with 70. Moving on to the following stage, we have the data element 70, and after comparing 70 with the search element, there is a match. We will now have the searching and display index as 4, and this index contains the searched element. We now comprehend the pseudocode of the linear search algorithm after learning the working terminology of linear search algorithm. First, we have a function called linear search, which has two variables in its parameters: the array's name, which is an array, and the search variable, which is the value. Then, using a for loop, we must search for our target variable by analyzing all the data elements in the dataset with the condition that is the searched item is identical to any set's value. We must return its index value. Now we must stop searching once the searched value has been discovered. Then we will close our if and for loop as well as the linear search function. We will now look into the complexity of linear search algorithm after comprehending the pseudocode. The complexity of linear search algorithm is divided into three categories: the best case, which is the big O of 1, the average case, which is the big O of capital N, and the worst case scenario, which is same as the average case, which is the big O of N. Here, N is the number of data items to be sorted. Let us look into how all these complexities of linear search algorithm play out in detail. First, we have the best case, which is big O of n. As a result, the best case scenario happens when the searched element is found in the dataset's first block. As a result, the search takes a constant amount of time. Here is an example of an array with 50, 10, 40, 20, 30 as the elements. Now, our search element is 50, which is located in the first location of the array. Then, there's the typical case of linear search algorithm, which has big O of n and occurs when the search element is in the middle of the dataset or any point of the dataset. With the array containing the same search element 50, we can easily see that the element 50 is present in the center of the array at the location number 2. Finally, we have the worst case, which is big O of n, which is same as that of the average case of the linear search algorithm and happens when the search element is in the last block of the dataset. As a result of the number of searches required is proportional to the number of elements. As demonstrated in this example, the search element 50 is found in the last block of the array index, which is 4. In the next segment, we will look into some real-world instances of linear search algorithms. According to the first application of the linear search algorithm, linear search is particularly efficient when it comes to discovering a particular string. Next, we will look into the second application of linear search algorithm. When a data set has only few elements, linear search is the simplest to implement. The final real-world application of the linear search algorithm is with the help of telephone directory. You may find out the name of a person with the phone number 123. This can be implemented easily using linear search algorithm. Now, let us have a look at the linear search algorithm working in practical demonstration. So on my screen, we have an example for linear search algorithm. We have included 3 libraries: standard input output, standard library, and console input output library. Then we have entered the main function where we have declared an array with maximum size of 50 elements, a counter variable I, a variable named target where we would store our searched element, and finally num variable where the number of elements in the array is recorded. Then we have a printf function to ask the user how many items are there in the array, and then we use a scanf function to allow input from the keyboard. So we have added %d format specifier to the scanf function, which is used for numeric values and num variable. Then using a for loop, we will try to print all the items in the array starting with 0 and ending with num variable, which is the last element. Then we will enter our search element, which we want to find among all the elements of the array. And as previously said, we'll store the found element in the target variable. Following that, we will use the for loop to examine all the elements in the array. Then we use the if statement to check for the element is identical to our searched element or not. If the element is found, we exit the for loop and we will break the keyword. And if the target value's location is less than the number of elements in the array, then we will return the location. Otherwise, if the value location is greater than the number of elements in the array, then the search will be unsuccessful and we won't be able to find the searched element. Now we will compile this code and see the output. So there you go, the code got successfully compiled. Now it is asking for the number of elements in the array. Let me give us 5 elements. Now let us enter the elements into the array. Let us enter some random elements. Now we have entered the 5 elements. Let me provide the searched element as 2. Now we have found the target element to be found in the location 2. That is 0, 1 and 2. Yeah, 2 is located in the second index location. And with that, we have reached to the end of day 1. So far, we have learned the data structures. On day 2 of software development learning, we will reveal the next stage where you get to master the algorithms. Thanks for watching and don't forget to subscribe to stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.